Okay, welcome everybody to the Asia and Oceania session of the third International SDB Day. We're very pleased to have you here. Before proceeding, I would just like to thank the conference organizers. So that would be Philip Klinger and Christian Boedinger and Knut Hartmann, the session chairs, and all the speakers who have, I have to say, enthusiastically contributed to making this event. In particular, I would like to acknowledge the two keynote speakers, which is Commander Waterson of the Royal Australian Navy and Captain Yanuar of Pushi Drosal in Indonesia. Truly, thank you all. So now I would just like to say a few words by way of introduction with a few slides. I will be brief. I'm going to assume you can see my screen.
It works perfectly, Magnus. You can start.
Thank you. So I know that there are some grizzled old campaigners in the room. So, but briefly, what we're speaking about today, SDB, is satellite-derived bathymetry. So surveying the seafloor from space. So that means optical, passive, multi or hyperspectral sensors sitting on Earth orbiting platforms and allowing us to record sunlight that's bouncing off the seafloor, which gives us information on the seafloor and the water column depth, in other words, bathymetry. So that's what SDB is. And why you should be aware of it and consider it as part of your surveying toolkit. It's non-intrusive by the very nature of being light being recorded from a satellite platform. Rapid, in other words, you could map somewhere across the globe and have your data within 24 hours, much more difficult to do if you have to deploy a ship. It's very low cost, typically in the order of 5 to 10 orders of magnitude lower compared to traditional methods. And again, you can access locations that are remote or perhaps inaccessible for various reasons using this technology. The spatial and temporal continuity, so these are not transects, this is a raster grid, no interpolation. And the temporal continuity comes from the fact that the satellite keeps recording this location on the globe repeatedly. So you can get continuity in your measurements and even go back in time, say 10 years back, to get your SDB measurements. And finally, I view this as a complementary technique, so it's not intended to replace acoustic techniques or LiDAR, for example. It's part of the surveying toolkit. So that then is the brief overview of what SDB is. And what we've seen over the last 20 years as part of EOMAP and part of this journey is how the growing acceptance of this technology and the accelerating uptake of SDB globally. And here's a map showing locations where we have mapped SDB throughout the world. And it's because of this that we instituted the International SDB Day a few years ago. We felt that this new technology requires a forum where users and providers can learn, exchange, and discuss on this technology, and that there is this increasing demand to understand how it can be used, but also to develop the capabilities further. So with that in mind, in 2018, we had our inaugural SDB Day in the lakeside, in the Lake District of Bavaria in Germany. That was followed the next year at the Sunshine Coast of Queensland in Australia. And now this year, I dare say it's perhaps a bit less exotic as a location, but on the flip side, we can have a lot more people join us for this from all over the globe. We had a great turnout for the Americas and European session 2 weeks ago, and there are many of you here. It's really fantastic to see, so we hope that this we can reach even more people this way. So thank you all for coming and joining us today on this SDB Day. And I would now like to hand over to the session chair for session 1, which is Gabriela Alodia. She is a lecturer at the Hydrography Research Group Institute at the Technology Institute of Bandung in Indonesia. And she received her Cat A hydrographic surveyor specification in Bretagne in France in 2015, and currently doing her PhD with the University of Leeds. So with that, I welcome you all to this third SDB Day, and I hand over to Gabriela. Thank you very much.
Thank you, Magnus, for the introduction. As introduced, my name is Gabriela Alodia. I will be your host for the first and second sessions for today's seminar. In the first session, we will discuss about the SDB developments and the future technologies. We've got 6 speakers from different backgrounds, and the session will last for about 90 minutes. We will have a live Q&A session at the end of the session, but we also encourage you to ask questions through the Q&A or the chat box. So, without further ado, I will begin the session by introducing you to our first keynote speaker, Commander Chris Watterson from the Royal Australian Navy. I will read his short bio first. So, Commander Chris Watterson, RAN, is a specialist hydrographic surveyor in the Royal Australian Navy. He commanded the Survey Motor Launch HMAS Shepparton in 2008 to 2009, and the Hydrographic Survey Ships HMAS or HMAS Llewellyn and HMAS Melville in 2013 to 2015. In 2016, he was awarded a certification as Level 1 Hydrographic Surveyor through the Surveying and Spatial Sciences Institute and commenced working at the Australian Hydrographic Office, where he was responsible for planning and managing national hydrographic surveys. He helped to establish and implement Australia's National Civil Survey Scheme, the Hydro Scheme and Industry Partnerships Program, and the AHO representative to OCBAT, the National Seabed Mapping Coordination Program. And in 2019, he moved to the Maritime Geospatial Program within the AHO, where he oversaw the acquisition and introduction into service of the AHO's satellite-derived bathymetry capability. So, Commander Chris Watterson, the floor is yours.
SDB is possibly the newest development in hydrographic surveying, and this is a very exciting time to be involved with this technology, as collectively, we, as a community of SDB users, are shaping the future of this technology, as we both learn and develop the technology, techniques and applications for SDB. Today, I want to share with you our SDB journey, to look at what we have learned, and to lay out some of the challenges we've faced in working with SDB. My journey began back in mid-2016 when discussion in defence, scientific and hydrographic circles about the advances in SDB generated sufficient interest for us to look further into the techniques and technology in this field. My first contact was a small meeting hosted by the Australian Hydrographic Office with industry, our national scientific and geospatial agencies to build our own understanding of both what SDB could do and the different offerings that were available on the market. Not long after this meeting, we received our first SDB software package and started separately purchasing processed SDB datasets under contract. Our initial experience with playing with SDB was a very steep learning curve. It wasn't just as simple as acquiring an image of a location and pressing start. Image quality, cloud, stability, satellite geometry all played a part and frustrated some of our early efforts. It became the case that we could spend days searching for a good image and only for a few hours of processing. We also learned that the results of an individual operator for a given scene could be vastly different from a second operator because they're using their own settings, adjustments and processing parameters. But again, we learned more as we progressed, and by working with our partners, refined our own processes to improve the consistency and quality of our outputs. Now, I'm pretty sure some of us thought in those days that commercial acquisition of satellite-derived bathymetric data was much easier than doing the work for ourselves. But that was also a trigger for us. We liked what we thought could be done with the Watcor-X software package and decided that we wanted to have that package for ourselves so we could do our own SDB. After some commercial negotiation and a very lengthy government procurement process, we became the first organisation in the world to acquire a Watcor-X licence. Now, being the first customer for anything can go one of two ways, and I'm pleased to say that our experience has been positive. We worked very closely with EOMAP to ensure that the software package we were using worked the way we wanted. So even prior to delivery, we'd given a very lengthy wish list to EOMAP of the functions that we thought would be good in the software. And we were able to work together and bounce ideas off each other to help to find some new applications and ways to use this technology. Our initial focus for SDB was purely for defence planning. We saw SDB as a tool to process imagery and collect hydrographic data. But the more we played with the data and technology, we could see the potential for SDB in so many other ways. It grew from a straight data acquisition tool to a survey planning tool and a risk reduction tool. Not only that, the technology behind SDB helped us to automate other charting processes. Now, at this point, let me acknowledge the work of others who went before us in this field. Around the same time that we started actively using SDB, the UKHO had already published their first chart containing SDB as a source survey. This was particularly significant within the hydrographic world, as it demonstrated acceptance of this technology by possibly the most influential agency in our field, and helped support our own case within my organisation to work with this technology. As hydrographic surveyors, we seek to prove the accuracy of any data collected, and hydrographic officers take a very conservative approach to publishing any survey data. So the fact that the UKHO had incorporated SDB into a chart was a major step to accepting this type of data within our own organisation. Possibly one of the biggest challenges has been the assessment and acceptance of the accuracy of SDB data. The horizontal accuracy of satellite positioning systems is widely accepted, so thankfully it doesn't take much discussion. The more challenging conversations have been held around the vertical accuracy or uncertainty of SDB data. In order to prove the accuracy of SDB for our own organisation, we ran numerous comparisons between SDB data against both LiDAR and multi-beam across a range of locations to prove the capability. We learned a lot from these comparisons, but significantly, we learned that where we had sufficient comparison or crossover data, we were able to tie the SDB to accepted depth information and improve the confidence and vertical accuracy of our data. As a broad generalisation, we describe SDB data as meeting IHO ZOC specifications, which are really quite generous. We view SDB as being around the 2 metre plus a percentage of water depth for vertical accuracy in the absence of supporting or comparative data. But where we have existing data in an area that can be compared against the SDB, we have the ability to refine the accuracy calculation and our own confidence in that assessment. And where the data supports this, we're comfortable that we can demonstrate accuracy supporting ZOC-B. I think it's also a significant advance that the most recent edition of the IHO Standards for Hydrographic Surveys publication S44 references SDB as a method for determining depth. This shows me that there's now growing acceptance globally of what SDB can offer. We've had to work hard within our organisation to build acceptance of the data and to educate users about the capabilities and also the limitations of SDB data, and we've had a few hurdles along this way. We've been using SDB as a survey planning tool to support our national survey program, and we've used this in a couple of ways. We initially saw SDB as an opportunity to reduce the risk of grounding for our survey ships, particularly if we could provide shape files or overlays for their navigation systems to help in the avoidance of dangers. Now, prior to every survey, we process the survey area with SDB at the planning stage to help in this risk reduction. But there was another factor to this. When we started looking at contracted surveys, we had to ensure that we were getting the best bang for buck for our survey dollars. This worked in a number of ways. First, we could identify the shallower parts of a prospective survey area. We were then able to focus our survey efforts on the parts that were navigationally significant, which helps us to reduce our costs. And secondly, it enabled us to make better, more refined a priori assessments of a survey area, which in turn helped to ensure that we were realising the best value in terms of survey line planning to most efficiently survey an area. To demonstrate the cost savings that SDB can achieve, I'll point to my own calculations for the entire coastline of Australia. If we were to look at mapping our entire EEZ, we estimate that there's in the order of 10.8 million survey line miles. Now, breaking that down further, in the 2 to 5 metre depth band, there's 1.6 million survey line miles and another 2.4 million survey line miles in the 5 to 15 metre depth band. if we could even cover just 1/4 of that shallow zone using SDB, based on the current going rates for physical survey data acquisition, we could save in the region of $1 billion on our own national survey program. When you take it from that perspective, the value proposition of SDB, whether commercially purchased data or the cost of a software license, when compared against survey line mile costs or the daily running costs of owning a survey fleet, becomes a very simple conversation. Now, as we started providing this data to our planning and contracting teams within the office, we occasionally hit some challenges. This was particularly the case in areas where we had overlapping survey data from a previous survey. And the survey planning team could see differences between the depth accuracy in SDB and what we had processed from their data. This is particularly the case around reef edges or steep slopes. As we know, SDB is dependent on the water properties for a quality return, and uniquely the resolution of the image, which can lead to pronounced edge effects. When we're using lower resolution imagery, this can lead to an edge effect where the steep slope of the reef edge is exaggerated seawards, and in this case is predominantly essentially a horizontal positioning error in the SDB spot sounding. The quality of the SDB data will drop off significantly as water quality varies and the complexity of the seabed varies, but that will not be readily evident in the SDB data. SDB data with sparse coverage or on the edge of extinction depths should be treated with some caution. As we've collected and processed SDB data, we've provided this to our charting section in our office, but this has also had challenges for incorporating the data into our national deconflicted bathymetric database. Firstly, our data managers weren't prepared for handling SDB data and had to develop new procedures for prioritising and deconflicting data. One of the issues we discovered was that when we processed 10-metre resolution imagery into a 10-metre resolution bathymetric surface, it became confusing for our cartographers, as the 10-metre bathymetric surface appears visually very similar to a thinned-down, high-resolution multi-beam dataset. We eventually overcame this by rendering 10-metre imagery as a 1-metre surface, which then shows SDB as spot soundings within the database and helps our cartographers visualise the difference. The next issue we faced with SDB data in our system was that data managers were in some cases ignoring SDB data because the ZOC allocated to a specific data set was lower than the other data in that database. We've overcome this by revising our data deconfliction procedures. Now, as we started playing around with Watcor-X, one of the really clever guys that works in my team worked out that the land masking feature would work well as a coastlining or feature delineation tool. And after a bit of playing around and some script writing, he demonstrated that the land masking feature could indeed extract a coastline for a survey area and export that as a shapefile. To understand the significance of this functionality, it helps to consider how nautical charting has advanced over the last few decades. When I started navigating ships, we were still using paper charts, and GPS positioning was a relatively new technology. Charts were a combination of metric and fathoms charts and were often on different datums. As the world moved towards electronic charting and ENC started being released, there was a race by hydrographic offices around the world to convert all of their charts to metric and WGS 84. The problem with this was the conversion process to fit the WGS 84 datum was not always straightforward, and as a result, old coastline data was at times stretched or compressed to fit corresponding reference points. Further, much of the old coastline data, especially in remote areas, was based on sketch surveys. The result is in many cases, you would end up with features that were literally a mile out of position. So for a hydrographic office, understanding that some of the legacies that have carried over from older charts, we wanted to prove the assurance that there weren't any nasty surprises in critical navigation areas. In order for us to make this happen, we purchased some commercial SDB data sets in key shipping areas to confirm the positioning of features, which has given us the confidence to know that the dangers are actually where we say they are. But also it's come from challenges for our cartographers because they've had to work out how to manage shifting features that were potentially an old feature on an existing chart and making sure there wasn't a blank space left behind. Another area that we were naturally drawn to with SDB was the potential for SDB in humanitarian assistance and disaster relief. From a Defence Force perspective, we are often called upon to assist following natural disasters such as cyclones, and SDB seems like an obvious solution to find a way to navigate in remote areas to enable aid to reach those in need. My team did some really great work over the last few weeks helping to find access routes for our ships working around Fiji to get them to where they were needed the most. Now, I've encountered the argument that immediately after an event, SDB will likely be of little use as the water quality will be too turbid or too rough, or there'll be too much cloud. And I agree there's the potential for that to happen. But in remote locations where you have sparse data, SDB from earlier imagery will help to identify likely landing locations, which means we can refine and focus our physical pre-landing survey areas and therefore reduce the time frame for us to start delivering help when it's needed the most. Remember that in this line of work there is no single solution, and SDB still has to be viewed as a complementary technology to traditional survey techniques. Also, if you consider the work that's just been completed in Fiji, we were still providing SDB support 3 to 4 weeks after the event, meaning that the age of imagery was not an issue, particularly as time moved on after the event. As word has started to spread within our own Defence Force about the capabilities and possibilities of SDB, we've started to see an increasing number of requests for SDB from our fleet, including for applications we hadn't thought of. There are the requests you might expect for things like landing data for amphibious exercises, but we've also seen navigators asking for route assurance in remote and poorly surveyed areas. In the same way that we do risk reduction for our survey teams, we're now seeing risk reduction for remote area transits. We're also receiving numerous requests from our scientific agencies for high resolution data to aid in environmental modelling for things like wave prediction on beaches. Within our immediate region, I think that SDB has a bright future. The Indian Pacific region presents ideal conditions for SDB, particularly in terms of water quality and visibility. We've seen commercial surveys undertaken in the last few years that have shown the viability and effectiveness of SDB, particularly as a complementary technology to established physical survey methods. Within our own office, we've recently moved from a trial to full production capability that supports both our national charting and military functions. There's a large body of work ahead of us as we grow that capability and start to build our data through SDB. Moving forward though, there are still opportunities for SDB to grow, and I pose the challenge to this audience. We're still challenged by surveying our polar regions, and SDB might offer a potential solution to help to derive the answer, or even using another form of remote sensing technology. There's enough progress on drones and cameras that I think this might be the way to improve accuracy or resolution of the work happening with SDB. I also think that change detection will be another likely area for growth for SDB, particularly in coastal and environmental monitoring. From my few years of being involved with SDB, this has been an exciting time with numerous and rapid developments. When you consider the survey coverage that can be achieved by SDB and the relative cost involved, there is a very clear future for SDB, and I look forward to the advances that we will see in this field over the next few years.
Thank you very much, Commander. Now I would like to introduce you to our second keynote speaker, Captain Yanuar Handwiono from PUS Hidrosal, or the Indonesian Naval Hydrographic and Oceanographic Center. I will read her short bio first. So, Captain Yanuar Handwiono is a specialist hydrographic surveyor in the Indonesian Naval Hydrographic and Oceanographic Center. He begins his career as a hydrographic officer on a naval hydrographic survey vessel since 1988. He has been undertaken various professional courses in hydrography since then. He awarded Caie surveyor in 1999 and commenced working at the Indonesian Naval Hydrographic and Oceanographic Center, where he was responsible for international cooperation and maritime boundaries. He is also a member of Indonesia's Maritime Boundaries Delegation Expert and participated actively in many IHO events, working group, and capacity building programs. He contributed greatly to the establishment of the Indonesian Marine Spatial Data Infrastructure, known as iMagic Portal, and optimizing the use of remote sensing technology, such as satellite imagery implementation in supporting hydrographic survey operations, disaster mitigations, and marine protection area mapping. In 2008, he was involved in the satellite-derived bathymetry implementation in the Indonesian Naval Hydrographic and Oceanographic Center as part of the iMagic Marine Geospatial Capability Program Development. So without further ado, Captain Yanuar, the floor is yours.
Thank you, Gabriela, for a very nice opening. For my presentation this time in my turns, I would like to share our experience and also developments in SDB application in our office, especially in updating our remotely area, which cannot be reached in the short ways, and also some of the implementation for environmentals and delimitations. Good morning, panelists and participants of the third SDB Day International Conference on Satellite-Derived Bathymetry. I'm Captain Yanuar from Indonesia Hydrographic Oceanography Centers, and it's been an honor for me to have opportunity to present in this respectful conference. In these occasions, allow me to deliver my presentation with titles Satellite-Derived Bathymetry Application for National Hydrographic Services. The growing demand of the bathymetric data for various marine applications have increased dramatically in the past few decades, and satellite-derived bathymetry became a choice which gives a lower cost method compared to the conventional techniques and fast bathymetry acquisition with larger coverage area. Satellite-derived bathymetry also can give high-resolution imagery to update and verify bathymetry data and cover remote areas. Satellite data bathymetry also can become alternative technique of collecting data rapidly by exploiting satellite imagery for charting purposes. For the mapping purposes, satellite-derived bathymetry is one of the techniques in remote sensing for extraction of the ocean depth by utilizing optical imagery, which has advantages that can be done completely remote, no environmental impacts or risk to personnel and equipments, no permitting or mobilization required, cost-effective and time-efficient, and useful for change detections of the shoals or shallow area. The disadvantage of this system is the coarse resolution compared to multi-beam echo sounders and LiDAR is around 2 meters versus centimeters, and not SOLAS compliant and can't be used for official safety of navigations. And at the other side, also not suitable for regions with persistent turbidity, and no official ISO standard exists for the SDB yet. In the implementation and usage for the safety of navigations up to now, there is no regulations that defines for the SDB implementations for the nautical chart. Refer to the ISO IOC CAPCO cookbook, which is explain the steps and methods and techniques and software used to procedure SDB data properly still can be used as the guidance in order to apply this technology for the safety navigation charting. As at the ISO IOC CAPCO cookbook, chapter 11 mentioned that this chapter describes the SDB procedure step by step using Landsat 8 imagery, and the procedure is described in an S3 ArcMap environment and includes the following key steps in the satellite-derived bathymetry procedures. The presentations of the data processed from the Landsat 8 and Sentinel-2 data as shown on the screens, which we can extract the shallow area and also shoals from the satellite-derived bathymetry, but we still cannot get the deeper depth or bathymetry presentations. Even though there is a limitations, but SDB data quality for nautical charters still can give a good coverage, even not as good as the multi-beam echo sounders, but still better than single-beam echo sounders and lead-line surveys, and still better object insonification or identification than lead-line, but not better than single-beam with the single-side sense sonar or multi-beam. The SDB also has a good positional accuracy, same with the multi-beam echo sounder and single-beam echo sounders. Even lesser depth accuracy not better than multi-beam echo sounders and single-beam echo sounders, and even with the lead line. But the SDBs can provide fast bathymetry acquisitions with large coverage area. Mentioning about the international regulation and standardizations, formally there is still no standard criteria defined for SDB depictions of the SDB data on nautical chart. In the standard publication S4 ISO has not mentioned the standardization of the SDB data and explained the provision of SDB data on the chart. But the method of provision of SDB data still can be referring to the ISO IOC CAPCO cookbook, ISO publication B11, and IOC manuals and guides. In Pusidosal or Indonesian Hydro-Oceanographic Centers, the SDB implementation using the SDB application software provided by EOMAP with a version of Watcor-X, which is in this applications, we still use the Landsat 8 with 8 pixel resolutions, 30 meters, and Sentinel with 2 pixels resolution to 10 meters. And for results, estimate the bathymetry penetration model up to 10 meters in the format vector SYZ. In Indonesian's hydrographic office, up to now, there is still ongoing process using the SDB technology, which targeted 300 areas in 2020 with total 200 kilometers square coverage area and approximately 60,000 kilometers square area can be covered in a year. The sequence of the process of the SDB application started with the satellite imagery and then converted it into SDB image by using the SDB software processing. And the end results, as shown on the screen, become the SDB depth extractions analysis, which is cover the shoals area and shallow area at the certain conditions of areas. The samples of the application for nautical chart updates, if we do the coverage comparisons, for the implementation of the SDB for nautical chart based on the area selections that needs up-to-date by prioritizing navigational hazard or danger to navigation informations, especially shoal area in the nautical chart, compared to modern survey methods such as single-beam echo sounder and multi-beam echo sounders with certain scales with length and width as we see, it will take longer times to cover such area compared using the SDB technology. The SDB technology can provide a rapid bathymetry observations and data compared to the other methodology. But even though it can do it fast, but there is still limitation in depth penetrations that related to the water clarity. In current SDB implementation in Indonesian nautical chart, the first Indonesian chart, which includes SDB data, can be seen as you see on the screen at the Indonesian chart number 373, where is the area in this chart. We have no survey data had been carried out and no data available yet. But by using the SDB, the shoal changes still can be detected, and we can use it as part of the updated for the nautical chart in that area. And in this implementation, we put on annotations which consist of how the depth presentations methodology were used. In this matter, we use a satellite-derived bathymetries, and then we put in the chart, and also how the shoals area are depicted with the different colors. In this matter, we use the blue colors without counters, which means that have been derived from satellite imagery, and uncharted danger may still can be exist. The other samples of the uses for the safety navigation is to identify the changes of the shoals and also the obstructions area. Is that we can identify these obstructions much more easily, visually from the satellite imagery, which can cover remote area and analyze which area are potentially has dangerous features to navigation and get the depth and dimensions without going to the sites. In current implementations for Indonesian nautical chart, we are also doing the shoal identification for some of the remote area, that using the SDB data, we can feel some remote coastal shallow water area which never had known depth before, and by using the SDB data, we can be put in, but still has to put on note in the nautical chart how the depth contour was measured and also what is the methodology, and presented with the blue colors as agreed by the cartographers. In another application, we also use the satellite-derived bathymetry to update the area, especially to make a modeling of the features changes in nautical chart. System imagery can also show the changes in color coding and make the shoal analysis become much more easy. We can identify the shoal area, the land developments, and also filtering within the noise and the real reflectance. For these identifications and investigations, we applied this methodology for updating the Indonesian chart number 318 with a scale 1 to 200,000. Another application of the SDB also used in our office in order to mapping and modeling the conservation areas. For these samples, we use the Wakatobi Marine National Park, where we use the SDB process and interpretation in color image for the SDB model, we shown the depth contour and the area, and we compare to the Indonesian chart number 137, the area figures with the SDB model when it was overlaid with the previous survey at chart 137, the area figures of the SDB model is still very precise and mostly similar shape to the figure at the chart with the green colors. So the SDBs also can be used to identify the changes, but at the other side, we believe there is still some accuracy for the shallow and shoals area. Since 2018, for the limitation process, we also developed the capability in using
Captain Yanuar, may I interrupt? The screen share has stopped.
Screen share. For the base point verification, we use the data for identifying the low tide coast to resolve maritime boundary disputes within the states by identifying the coastline used to generate the median line. At the other side, for the base point verification in determining enclave claims, low waterline contour points are needed through satellite-derived bathymetry. As shown on the screens, this is how we implemented the satellite-derived bathymetry in order to do the verifications of our base points related to the contour, especially the low waterline contours. As the conclusions, the usage of SDB data is giving wider coverage and opportunity to analyze and identify shoals area, navigational hazard, obstructions, especially in making comparison between data of the previous survey or against the present satellite imagery. The SDB data processing still need other data source for comparisons, and its method can be sounding data, but still can be used for certain chart update purposes, even though errors or uncertainty still increase with the increasing depth. And for tropical area, water quality still become the limitations. Based on the UKHO study, only a depth under 15 meters is considered good, so such result will be different with different area and satellite image, and depends on the ground truth data. Although SDB does not meet S44, but most of the results have been categorized to Cancel C and still better than lead line survey. In Indonesia, the implementation results also vary in certain areas related to the seawater clarity, especially at the coastal area which has estuary and some area which has dense materials and dark. In practical so far, SDB accuracy can reach about 2 through 3 meters accuracy. And from our perspective, the SDB implementation has potential future usage in charting update process and in supporting coastal management policy, since the technology can make analysis become faster with wider area coverage in effective ways. This is the end of my presentations. Thank you for the attentions, and allow me to give back floor to our moderator, Ms. Gabriela. Thank you and good morning. Thank you, Gabriela. I'm sorry for some technical mistakes, and hopefully you still can enjoy the presentations, and hopefully the others can understand, because some of the data sometimes the link is not convenient here. Thank you, Gabriela, for the times.
Right. Thank you very much, Captain. As I have informed you in the beginning, if you've got any questions, you can always address the question either in the chat box or in the Q&A box. I will read your questions in the Q&A session at the end of this first session. Okay, now we will move on with the talks. So the first talk after the keynotes, the first talk would be delivered by Dr. Chris Roelfsema from University of Queensland. And he will be delivering a talk that is titled, How much coral habitat is there on the Great Barrier Reef and why is depth so important? So before we move on with the talk, I will again read you his short bio. So Dr. Chris Roelfsema is a senior researcher at the University of Queensland. He leads a team of ecologists and Earth observation specialists with collecting field data and developing and implementing habitat mapping and monitoring approaches. With 20 years of experience, he is specialized in integrating field data, citizen science, physical attributes, for example, the depth and the waves, and Earth observation science to map and monitor coral reef and seagrass habitats globally. He is currently the principal investigator on 2 major coral reef habitat mapping projects. The first one is the 3D GBR habitat mapping project, and the second one is the Global Coral Reef Mapping Project for the Allen Coral Atlas. It sounds very, very interesting. So Dr. Chris Roelfsema, I believe that you will deliver your presentation live.
Yes.
Yes, okay. Just a reminder, I will give you 3 minutes when you have 3 minutes left. So I will give you a reminder and you will have 13 minutes for your whole presentation. Okay.
Okay, good. Can everybody hear me and see my presentation?
Yes,
very
clear now.
Okay, good. So thanks all for being present at this presentation. It's very impressive how many people attend. It's really great. And in the previous talks, it was shown how the bathymetry from satellite was used or integrated in government agencies and in coastal mapping of the nautical charts and so on. And I realized that 2 gentlemen had a strong hydrographic background, and I had to realize that I actually have a hydrographic background as well. I did hydrography at the Hydrographic Nautical School in Amsterdam, and then did a degree in geodetic engineering, and then got specialized in coral reef remote sensing at the University of Queensland. And obviously my talk is about coral reef remote sensing, and I focus in this case on specifically the Great Barrier Reef, but we'll mention a bit about the global mapping as well. And I will focus on how remote sensing is important, satellite bathymetry is important. Obviously, this is work done with many different people and different organizations responsible for it, and I have to acknowledge all their input, or like to acknowledge. So first of all, coral reef scientists and managers require habitat maps to know and how it's changing and how to conserve and monitor these environments. Here you see an example of a piece of satellite imagery of one of the reefs we've been working. If you would go underwater, you would see in detail the algae, the rock, rubble, sand, seagrass, and corals that make up these reefs. And there's 231,000 reefs at this stage in the world. So it's a massive area. These reefs, you can look at the benthos, so these algae, coral, and seagrass, and those are the benthic maps I'll be talking about. But you can also map them at geomorphic level. And you talk about the coral caye, the lagoons, the reef flat, the crest, and the slope. And a simple way to say the importance, like if on the moment you know where the busy areas where most people are, then you also know where the most resources are needed. And on the moment you map the reef crest and the reef slope, you get a better idea where the busy area of the reef is compared to the rural area. That doesn't mean that the rural area is not important, but it gives you an idea how marine scientists and biologists are using these type of maps. And I'll give you some examples of that. Coral reef maps can be made at different levels, and I keep on introducing this slide to just take care we're all at the same level. You can look at reef systems where you look at a group of reefs, 20, 30, hundreds of reefs, where you see here an individual reef. You can look at reef types, and these that can be fringing reef, barrier reef, lagoonal reef. You can look at the different geomorphic zones within a reef that represent the different characteristics of a reef. And then you can look at benthic community, sand dominant, algae dominant, or coral dominant. Satellite and airborne imagery can be used to map these environments using the texture, the color, but also physical attributes such as depth, slopes, and waves, and neighborhood relationships as well. So with our work that's been developed over the last 20 years, we developed an approach that we could map large reef systems without going to every single reef. That work started on the little reef on the south of the Great Barrier Reef called Heron, and we've done annual work there, ongoing, and learned a lot of our techniques. Then we were lucky to get funded to look at mapping large reef areas, so 20 reefs in the Capricorn to 237 reefs in the Cairns region. And obviously you can't go to every single reef. That would be nice, but it's not possible in this time frame due to resources. Then we, as a result of this work, we got asked to map all the reefs of the Great Barrier Reef to even coral type level, but also asked by Vulcan Philanthropic, the late Paul Allen, who is co-founder of Microsoft. His team asked us to get involved in mapping all the reefs of the world. Both projects are still going ahead side to side. To map an environment, doesn't matter if it's on the water or above, it's important that you have a good classification scheme. That classification scheme helps define the different features you are trying to map, and also try to show how they differentiate from each other. In that classification scheme, in the approach we are using, we also look at the physical attributes. So here you see a graph table. On the y-axis you see the, or y-axis on the, this column you see the geomorphic zones, and in the rows, and in the columns you see the different physical attribute. And depth is a very important one because it also defines slopes and phase. And on the moment you have a depth profile, you actually can see where the different geomorphic zones fit in. So yeah, depth and slope help differentiate those classes and as well. So our mapping approach uses as input satellite imagery and field data, and traditionally that was usually the most you did. But we decided to put knowledge in it of our understanding of the reef, meaning also water depth, waves, slope, and also training data to help create the maps. And our knowledge is, so for instance, yeah, slope, if a slope is a slope, if it's sloping. So if you have good depth, you can determine slope. So with satellite imagery, you can derive water depth. There's nothing new. And for me, that's an accepted fact that I will greatly use for the research that we are doing. On the moment you have this detailed water depth that come from satellite imagery, then you have wind data, you can actually also create very detailed wave height models. Again, and they often are dependent, not always, but often are dependent on depth as well, and the fetch. So from the satellite product, there's directly water depth coming, but slope and wave height that we can use for our work. So for the Great Barrier Reef, for the mapping we're doing there, we have geolocated photos, collected 100,000 photos, collected over the reef, analyzed for benthic composition. We use Sentinel-2 satellite data, and with the help of EOMAP, they created for us an absolute depth bathymetry layer. which is a really high level of detail and value for our work. As a result of the absolute depth, we could create a very detailed local wave climate model with 18 different parameters describing the waves. We could calculate absolute slope as well. And then with our geomorphic training data, we created what we call a Google Earth in what's known as Google Earth Engine, an approach where we first integrate the data and combine it, then apply a random forest classifier, then do object-based cleanup, and then an accuracy assessment. In the random forest, the absolute depth, the absolute slope, and the waves are a layer that are used in that classifier together with the satellite imagery. In the object-based cleanup, we use depth, for instance, to differentiate between shallow lagoon and deep lagoon using hard thresholds, especially because it's absolute depth. And we use to differentiate between sloping areas and non-sloping areas. So that gives us extra values to get really good maps out of it. So yeah, that's all approach, and that, again, depth, slope, and waves are really important for that process. Now we also predict coral types, and to predict coral types, you need to know slope, you need to know depth, and the waves to predict that on the slopes. So again, another location where it's used. That resulted in a now, which is going to be public in this month's global habitat map of the whole Great Barrier Reef, the first one of its kind. It's never done before at this level of detail. And you can see that the map created, the gray one, the box, gives you the surface area of the reef based on the old data, which in unknown depth. We don't know exactly to what depth it is, but it provides us a bit of an idea how much surface area there is, horizontal projected. With the geomorphic maps, we can look at up to 20 meters what the composition is. Up to 3 meters we could also look, because we can look at any depth, and we can also look at the different benthic, what the composition. All these three values for the whole GBR or for every single reef on the GBR has not been able to be represented before, and it's the first of its kind. And again, depth was consistent in there. If you look at existing maps, they show here the area, and here you can see that with our maps you can see more detail. But you can use depth again to do cutoffs of only showing up to 10 meters or 20 meters, whatever. But using the three-dimensional capacity of the imagery combined with the water depth, we can actually do more. And if you look at this three-dimensional version of the map plotted on top of the profile, you can say that if you know the horizontal projected area, now with the depth, you actually know also what the surface area is. And knowing that, we realize that the increase of surface area of reef by knowing this depth is significant.
Yeah, you've got 3 more minutes, sir.
Thank you. So it's twice as much area that is available could be used in our calculation to understand reef environment. You can do that at the whole reef level, but you could do that also at the different geomorphic zones. And you can see that for the slopes, there's an increase of 4 to 5 times as much surface area where coral could grow on or be present. You can do that for the benthic, but these are just really simple calculations that we now can do over the whole reef and get a better understanding of what's available. To the extent that you can calculate the surface area of what area is suitable for coral habitat, for instance, each of these management zones that the Great Barrier Reef Marine Park is using. Again, a lot of detail and depth is crucial. Now, to put it up a notch, with all these different data sets and these approaches we've been developing in collaboration with the Great Barrier Reef Marine Park Authority, but also with Vulcan Philanthropic, with the Allen Coral Atlas was created. And that's basically work which is ongoing, where we divided the world in mapping regions. And for each region, we get a low-tide planet dove mosaic. And with the help of the Arizona State University, they created relative depth. So it's not absolute, and it definitely makes a difference. We have global wave model, and we have relative slope as well. And again, that directly feeds into it. So that gets to the end of my talk. And basically, the maps will be available soon. It shows geomorphic, benthic, and coral type. It's publicly accessible, open source, anybody can use it. And there's no doubt about it that we could not get these good habitat maps if we wouldn't use depth to help differentiate between the different mapping features. And again, it's not only used on the Great Barrier Reef, but also for global mapping. So yeah, thanks for listening. And if you have questions, please leave them at the end.
Okay, thank you very much, Dr. Roelfsema. So we've got a representation both from the Navy officers and from the researchers. Now we will move on to our next speaker, Emily Twiggs from EOMAP Australia, which will present to you about the SDB use cases in Oceania. I will read her bio first. So Emily Twiggs is a senior project manager of EOMAP Australia. She is a geoscientist that represents EOMAP throughout the Australasia region. Originally from England, Emily moved to Australia 20 years ago after completing her degree in geological sciences. During her time traveling around Australia, Emily became a dive master and whale shark spotter on the Ningaloo Reef, an experience which cemented her love for the ocean and marine sciences. For the last 15 years, Emily has gained a broad range of experience during her PhD research and work life in the Curtin University, the Australian Institute of Marine Science, and Fugro Airborne Surveys, in using remote sensing and geospatial analysis alongside ground truthing techniques to map the bathymetry, geomorphology, sedimentology, and benthic habitats of coastal, coral reef, continental shelf, and terrestrial environments. As the director of the OceanWise Australia, she also ran research-based whale, shark, and coral reef eco tours, educational programs, and environmental sciences services on the Ningaloo Coast World Heritage Area and elsewhere in Western Australia. For the last 2.5 years, Emily has been working as the senior project manager with EOMAP, based in Perth, and has been involved in many exciting mapping projects within the region. So without further ado, I will give the floor to Emily. Emily, the floor is yours.
Thank you, Gabriella. Let me just share. Hopefully you can see my talk. Is that coming through okay?
No, not yet.
Not yet.
Right.
So it should be there now.
No, not yet.
Okay, just double check. Okay.
No, it's fine.
Okay, brilliant. Thank you, Gabriella, for the intro, and hello everyone out there. I'll be doing a talk today on the satellite-derived bathymetry for the Oceania region. So we obviously have a huge range of different projects that we work on, and I'd like to give you a bit of a background on those. So as Magnus said, there's obviously seen, Magnus said earlier, we've seen a huge uptake at EOMAP in the number of projects that we've done in the last couple of years. There's been a huge uptake, so we've done around over 100 seafloor mapping projects in the last 2 years, and in over 25 countries. So we have a really diverse client group. We've got engineers, consultancies, governments, and academia. And globally, the projects that we work on, they're extremely diverse in their uses for SDB, and that's obviously no different in the region, in our Oceania region down here. So as you can see, some of the uses, which I will go through some of these examples. So hydrographic surveying, a massive uptake in that, as you've heard from the talks before me, where they can be used as, SDB can be used for reconnaissance, for gap filling between other survey data like multi-beam and LiDAR, and also to extend coverage as well where there's no other data. Coastal management, this is another area where we've seen lots of councils, local councils around Australia running coastal management programs using SDB. We've got the energy sector and mining operations, so SDBs using pipeline crossings, building jetties, safe passage of vessels, oceanographic activities where SDB can be used in hydrodynamic models, inundation modeling and biogeochemical modeling, environmental mapping. As Chris's talk just said, we can do baseline, geomorphic and habitat mapping and repeat mapping for monitoring. We have port operations, so lots of dredging programs and detecting change and infrastructure associated with those projects, and also for coastal development and maritime boundary disputes. We really need a detailed understanding of coastal morphology, and it's really crucial in cases like that, which often end up in international courts. So what I'll do is I'll actually go through some examples that we've been working on, and I'll start with hydrographic surveys. And I can't talk about hydrographic work without mentioning one of the largest hydrographic projects we've been involved with, and this was with Land Information New Zealand under the Regional Pacific Navigation Initiative, a collaboration between IXBlue and Geomatics Data Solutions, who are now part of WPRT. The aims of the project were to provide safe navigation in Pacific waters, a huge area sort of covering Tonga, Tokelau, and areas with Nui and the Cook Islands, obviously to protect fragile ocean environments, but also to allow Pacific economies to develop. It was the world's first survey to create a seamless data set of SDB with LiDAR and multi-beam data, and the SDB was originally initially used as a reconnaissance tool and planning tool. So we went in and we used 15-meter Landsat 8 imagery, and we went in and we did about 400,000 square kilometers, so a massive area. And then we went in and we did 2-meter resolution for around 6,500 kilometers squared. So we used WorldView 2, 3 and 4 sensors for that one, down to about 20 meters depth. The SDB was used as to fill gaps between the different data sets, but also to extend coverage where no other data was available. So LINZ updated their charts with a combined multi-sensor bathymetry, but also with the SDB alone. And there was obviously a huge cost saving and time saving exercise with all these three highly complementary technologies. Another hydrographic mapping project that we've done recently, but a lot different, a lot smaller. This is for the Takau and Nakumano Islands, which is a really remote area in PNG. Extreme risk of climate change. They're only 1 meter above sea level. So we were asked by the National Maritime Safety Authority to undertake, to aid in their safe navigation. And they also wanted to verify territorial baselines for PNG as well. So just an interesting fact, Nakumano is actually believed to be the last position of Amelia Earhart, who was trying to doing the first round the world flight by a woman back in 1937. Sadly, the plane is believed to have run out of fuel somewhere in this region. So it's a very remote area. We did 10-meter SDB, and also we did seafloor habitat classifications for this area. We used Sentinel-2 for about 355 square kilometers. And as you can see, it's obviously got lots of coral bommies and pinnacles, and it's a very tricky environment to navigate. So we did SBD down to about 25 meters water depth. So it was a perfect environment for doing SDB. Now, as I said before, coastal change, this is a really increasing area as well for coastal zone monitoring. This was a pilot study with Fugro for the city of Gold Coast in Queensland. They spend large amount of effort maintaining and protecting their beaches. And we're looking for a monitoring solution for looking at sand movement and morphological change along about a 30-kilometer stretch of coast that you can see there. Fugro, they're actually one of the first subscribers of our Eolytics SB SDB software. The EOMAP team will be talking about this in detail during session 2's do-it-yourself workshop, but just briefly, it allows clients to actually do their own SDB in-house with local survey data, and they use this data to train satellite imagery using a physics-based image analysis, but also the latest AI techniques. So SDB was at 10-meter resolution for this project using Sentinel-2. Maximum depths are around 15 meters, but they did different seasons, so it changed slightly. Now, LiDAR was initially used for the as a baseline to test the accuracy of the SDB, and there was a really, really good match, a mean difference of around 0.2 meters, as you can see on the right-hand side there. So single beam profiles, which they have set up, you can see 1, 2, 3, 4, and 5 profiles there. They were then used for subsequent training within the EOlytics SDB software for different times of year. And the SDB showed, you know, a really highly dynamic sea floor, lots of shore parallel movements, migration of all the sediment along shore, and it was possible, you can see on the right hand side, you could calculate sort of fills and losses for specific time ranges. So SDB is a great tool for coastal zone management applications. It's now being regularly used by many local councils around Australia and obviously beyond. And Fugro are using this EOlytics software as well, which allows you to do your own SDB. They're now using it for coastal management projects, but also for other projects like cable management landing sites throughout the world. So slightly different case. This is for mining infrastructure, and this was a project again in PNG, and it was a small project, just sort of 5 square kilometre areas, and we worked with Geopacific Resources. They're based out of Perth, my hometown, and they needed some very high resolution SDB for basically for infrastructure development and supporting decision making. And so this is as a background, back in 1895, gold was first discovered on this island, so it sort of sparked a massive gold rush from Queensland. So Geopacific are now currently developing a high margin gold project, and SDB will be needed to support obviously all the decisions around infrastructure. So they needed very, very high resolution, so the a 2-meter resolution using a WorldView 2 satellite down to about 14 meters water depth for 2 different areas on the island. Now, this is a really interesting one, which we did last year. So I don't know if you'll know, there's something called the Asian Renewable Energy Hub, and it's actually in Western Australia, up in the Pilbara, and it's going to be the largest wind and solar farm in the world, actually the largest power station on Earth. So it's located in the Pilbara, and it's a perfect desert site to capture wind and solar. It's going to provide around 26,000 megawatts of renewable energy using wind and solar, which will power mines and other industry in the region, but it will also create green ammonia, which can offset around 20 million tons of CO2 emissions every year, as well as having lots of other uses. So the area of interest for this project was just north of that, at 80 Mile Beach, for Intercontinental Energy we worked on the project with. And 80 Mile Beach, it's got a very big tidal range, about 8 meters, often very highly turbid, mobile sediments, lots of strong turbidity and tidal currents. So the question from Intercontinental was,
3 more minutes.
Okay, well, do we have sufficient depths in the center of the circle that you can see there for safe passage of boats? So we did 10-meter resolution SDB for around 315 square kilometers in 19 meters water depth. And they also had some single beam, which we could do an accuracy assessment. So it was a really great fit of around 97% values within about plus or minus 0.5 plus 10% of water depth compared to survey data. Now this is another one on our part of the world in WA. This was for defence, for an underwater training exercise. They currently have no facilities for demolition projects in Western Australia. Our forces have to go over east or overseas. So we worked with a consultancy called Eurocon based in Perth for their environmental review of this defence project, and the UTRs are going to be based at Swanbourne, which is my local beach. You can see that little circle there, that's actually my local beach, and to about an hour's north up at Lancelin. And this is for training of special forces, for WA Police, and for other national and international forces. So it is under environmental review at the moment. They needed their little footprint where they're going to do the destinations to be in sandy habitats away from seagrass. So we use 2 meter SDB using WorldView 2, and we mapped around 70 kilometers, squared map to around 18 meters at Swanbourne and about 22 meters depth at Lancelin. So this is a really fantastic project for oceanographic investigations, and we've just started this one. They've just finished part of the project doing the SDB. It's with the CSIRO, it's for the Climate Information Services for Resilient Development Vanuatu project, a bit of a mouthful. But basically CSIRO needed a lot more up-to-date bathymetry for the coastal zones. So we are doing 10 meter SDB for the entire region. And we're also doing a multi-source bathymetry grid for, it's around 209 square kilometers. So it's a very, very large area. This will be used for hydrodynamic surveys, for, hydrodynamic modeling for wave and biogeochemical modeling, amongst other things. So the team have already got stuck into this one, and we're really looking forward to getting this project complete for them very soon. Now, I'm nearly finished. Chris just talked about baseline mapping and monitoring of coral reefs. We've obviously just finished recently mapping the shallow waters of the entire Great Barrier Reef, and our sort of coral reef journey started on the west coast up at Ningaloo Reef about 15 years ago. So there's obviously a huge cost benefit to using multispectral satellite data and other airborne data, such as drone information and hyperspectral, just to map these reefs frequently and at various scales. Obviously essential for understanding impacts from things like climate change and other local impacts. So just to finish off, this is a really exciting development for shallow water mapping and automation. We'll obviously see the knock-on effects over in our region in the next couple of years. This is the EU-funded 4S, so it's the Satellite Seafloor Survey Suite, and it's got 3 main aims, mainly to automate Earth observation mapping and monitoring, so for habitat mapping, seafloor classifications, morphology of shallow water, and also new sensor and platform technologies, so creating algorithms for drone data, for satellite LiDAR systems and hyperspectral data, and to develop and improve some of the software tools that we already have in-house. So for the end user, it will be a simple to use cloud-based workflow. We'll use highly automated algorithms, and it will also use spectral information and the latest AI technology. We obviously need test imagery for these projects. We had some great imagery from consultancy in Perth called Oceania Australia. They did a lot of drone imagery up in Exmouth Gulf, which is near Ningaloo Reef, and drones is a big area that we're going into, and obviously it's perfect data. You can go down to, in this example, about 3 centimeter resolution. So, you can get right down to monitoring different individual coral heads. So that's a really, really exciting project. And I'm obviously going to be running out of time, so I will finish there. I do have to, so thank you for listening. Now, I won't be around for the Q&A session, unfortunately. COVID restrictions this week changed the first week of kindy for my little one, so I've got to go and pick him up soon. But if you do have any questions, please email me, and we can obviously start the conversation there too as well. So hope you enjoy the rest of the sessions, and back to you, Gabriella.
Thank you very much, Emily. So our next speaker would be Mr. Friedhelm Moggert-Kägeler from the 7 Seas. He will be presenting about detecting hidden shoals from space. Sounds very interesting. I will read his bio first. So Friedhelm Moggert-Kägeler is the Solutions Director of the Maritime Spatial Data. His educational background is geodesy or hydrography, and he holds a degree in each of these fields. He joined 7 Seas in 2000, and since then, his variety of roles has ranged from S57 data production and training customer support and research and development to product management. Now his responsibility is to develop strategies and solutions for products and services used to manage, analyze, and distribute maritime spatial data. Through long-term experience, Friedhelm has specialized expertise in the domain of electronic chart production and also in-depth knowledge of relevant IHO standards. He regularly represents 7 Seas at IHO working group meetings, industry conferences, and exhibitions. So for Mr. Friedhelm, I will also give you a 3 minutes reminder at the end of your presentation. So without further ado, the floor is yours.
Yes, good morning. Thanks, Gabriela, for these kind words. I guess I will first try to use the screen sharing function here in Zoom, and you may want to confirm if this works for everybody.
Mm-hmm.
So I understand
Yes.
that was a yes. Okay. Thank you. Yes, thanks for giving me the opportunity here at the SDB Day 2021 to do this presentation. A few words about 7 Seas and Chart World. So we are developing software, we are providing services and solutions dealing with electronic charts, with ACTIS. So Chart World has its own chart distribution service, a global service, which also includes nautical publications. So this presentation, so let's see if I can proceed here. It requires a couple of clicks on my keyboard here. Yeah, this presentation is about navigational charts, about the issue with navigational charts with respect to the accuracy. I also want to explain what Earth observation data has to do with it. I will introduce, provide some information about the pilot project we did on this subject. We will look into groundings and how they are related to this topic. And I will explain how we want to, from the pilot project, from the results of this pilot project, we want to start a global service dealing with shoal detection based on EU data. And finally, I will draw some conclusions. So the title is Detecting Hidden Shoals from Space. And I will start with some information about accuracy data in navigational charts. So basically, we heard about this in previous presentations, that the accuracy of depth information in nautical charts can vary from very good to very poor. There are reasons for this. So the quality depends on the age and the accuracy of an individual survey. Remote areas tend to be less surveyed and less frequently. Other reasons may be costs or other possibilities to access isolated regions. And so for the mariners, it's important to understand when they use an electronic chart that there's a specific schema indicating the accuracy of bathymetry, and the schema is referred to as CATZOC, Category Zone of Confidence. So this one here, and this is how it can be visualized on the chart. If you look on this example, there are areas with 3 stars, areas with 6 stars. So basically, it's like when you pick a hotel, the more stars are shown, the better the hotel. That's basically the same here with the charts. For the mariners, I mentioned it is very important to take this in consideration when they do planning and when they are actually sailing in these areas. And so one important aspect here is that this accuracy refers to a vertical component and to a horizontal component as well. We will come back to this later. The importance of the use of CATZOC becomes very evident when we look at some groundings that happened during the last couple of years and that we looked into. And very often we found that too little regard was given to CATSOC, and this contributed to the grounding. So there's a variety of reasons for grounding. It's not only one reason, but it was evident that there was an issue with the interpretation of CATSOC. And even though the hydrographic officers assigned a CATSOC, there were situations where vessels tried to pass obstructions with insufficient distance to do so. One issue here is the use of point symbols representing dangerous underwater obstructions. This sometimes led to wrong conclusions. If you look at this chart, at this zoom level here, you can see that this symbol has an extent of 1,000 meter. If we switch to a bigger zoom level, like we see it here, the symbol size itself doesn't change, but all of a sudden this 1,000 meter would cover this circular area. At this zoom level, this circle of 1,000 meters represents the accuracy of a CATSOC zone category C, which is represented by 3 stars, which means if you are sailing here with a ship and try to pass this obstruction, you may want to avoid it at least by this distance here. I guess it was in 2016 when we came across SDB, when we heard about it, and this was when we met our friends from EOMAP. And shortly after this, we even did a joint project, which was also a funded project called MARSAT. And this was the first time that we got in touch with SDB. And so what we understood and what we know about SDB now, has been said before, is that, yeah, we can derive bathymetry from optical satellite images under ideal conditions. It's possible to derive depths up to a maximum of 30 meters. The vertical accuracy of SDB data is okay. So we heard it before, it corresponds to CATSOC C, but we also heard that this may be problematic for nautical charting due to this not optimal accuracy on the vertical level. But then when we were looking deeper into the topic, it struck us that the horizontal accuracy of SDB data is much better. And so as I mentioned before, there's always a vertical component and a horizontal component. And the horizontal accuracy of SDB data is basically close to the resolution of the satellite imagery. And so we thought there must be something in this. So we had this idea that Earth observation data, satellite data, could be used for shoal detection. So the idea is that despite the fact that we cannot determine with the highest accuracy how deep a particular obstruction on the shoal is, we can pretty well determine its extent. And so we asked some questions. So is it possible to locate shoals in underwater rocks on the basis of satellite imagery? Can we extract the real extent of the features rather than just using a point symbol? Can we determine the position better than what we see in charts with a CATSOC C or worse? And what's very important, is it possible to make it visible to the mariner in the chart? Also, is it possible to connect it to ACTIS and make ACTIS aware of such shoals? So in order to answer all these questions, what you usually do is you run a pilot project. So we picked an area in Southeast Asia. We got in touch with our friends from EOMAP, and we were discussing this pilot project, and they were very, very helpful and supportive in this respect. So they extracted optical satellite images from the area and processed it, so that what we received was a vectorized data set showing or containing these obstructions, and that's what we would refer to as stay-away areas. So from the satellite images, basically EOMAP extracted shoals, obstructions, and provided it as in a vector format. We then took this data and incorporated the stay-away area features into a chart so that we can make it visible like it is shown here in this example. We did an analysis of the pilot project, of course, and during this analysis, we mainly compared the results with obstructions and shoals in the electronic charts. And we identified 4 categories of findings. First of all, there were shoals that were matching, which means at the location where the satellite images, when the satellite image, the obstructions or shoals were detected, like here, there was a charted obstruction in the ENC. The next one was that we also found uncharted shoals or obstructions, like in this example here. So this red area indicates an obstruction or a shoal that was not found in the chart. The third category are shoals and obstructions that are kind of misplaced, maybe due to a different datum that was used when the chart, horizontal datum when the chart was produced. So in this example, we see that actually these 2 little islands are at this location, like they are shown up here in the satellite image and in this in the stay-away areas. But there were also, Gabriela, is there an issue?
3 more minutes.
Okay, so I have to hurry up. There were also cases where we could not pick up the obstructions in the satellite data. This was due to the fact, or maybe that they were just too deep, or the satellite image was not suitable, or the water clarity was not sufficient. So, summary of the pilot project results: we detected in an area of 10 by 10 degree 4,700 shoals, and this does not necessarily mean that these are all considered to be obstructions, because many of the shoals were picked up close to the coastline in areas where ships usually don't go. But we also found 381 isolated dangers in ENCs, and only 92 could be matched, which means that the 92 were found in an ENC, and the remaining 289 could not be matched. So there were potentially at another location. The relevance of such an undertaking becomes clear when we look at groundings. On the left side, there's an example where we had real SDB data, high resolution, where we, at this position of this grounding, where the ship tried to pass this obstruction, we really detected that there was a shoal with all its detail. For the stay-away approach, we want to use 10-meter resolution data, which of course is not so expensive, which is freely available. And still, what we can do is we can catch the extent of such a shoal, such an obstruction, prior to the grounding. This could have been avoided. What we want to do is we were looking for suitable regions to set up a service, which is for stay-away areas, and there are 3 categories. First of all, we look at the CATSOC distribution. This only makes sense in CATSOC areas which are relatively bad. We look at the technical feasibility, so basically water clarity, and also at the vessel traffic density. This makes sense mainly in areas where the traffic density is sufficient. We define suitable regions based on this analysis, and at this stage we identified areas in the Caribbean and Southeast Asia, also in South Pacific, but the traffic density is not that big there. So give me one more minute, Gabriela. So our next goal is to make a global service out of this. So what we want to do is we want to build up a stay away area database and integrate it in ChartWorld's chart information overlay service. So what we can see now, that while this is a picture of the original electronic chart, if we have the stay away overlay, it becomes clearly see where a ship should go and where it should better not go. So far we have been looking at using stay away areas for voyage monitoring, but why don't we use it prior to the voyage, include stay away areas in voyage planning systems? So in our voyage planning system, a route network is a basis for an automated voyage planning system. And so what we can see here in these images on the right is that while the route network was designed like this in the first place, using stay away areas, we can see it's better that the limits of the route network are pushed here to the waters which are much safer. So I'm coming to the conclusions. So we learned that it's possible to extract shoals from satellite imagery. Items detected are potentially dangerous to marine navigation, so we just have to look at the groundings. I introduced two. There are a couple of more groundings. The results can be used to create charts showing stay away areas that should be avoided by vessels. So what we're not saying stay away areas will show everything, all the shoals, all the obstructions, but those that are picked up should be avoided. This is why we call it stay away. It can support automated voyage planning. And what we want to stress at this point is that stay away areas can be used as a complementary information to the information of the electronic chart. We do not want to replace the electronic chart, of course. So this is the end of my little presentation. I'd like to thank you much. Feel free to contact me via the chat or via email. And so I give it back to Gabriela. Thank you.
Thank you very much, Friedman. So our last speaker in the session would be Magnus Wettle. So we are going back to Magnus from EOMAP Australia, and his talk is going to be about the SDB trajectory, a brief history, recent applications, and SDB 2.0. So a short bio from Magnus. Magnus Wettle is the Managing Director of EOMAP Australia. He has more than 17 years experience in aquatic remote sensing research and applied solutions. During his career at CSIRO, he co-developed the Sambuca software, which is used today by CSIRO for shallow water applications. While at Geoscience Australia, he led the implementation of new capabilities such as satellite-based bathymetry and offshore oil seep detection. As a senior research fellow at the University of Queensland, he managed the delivery of multidisciplinary remote sensing-based solution to the natural resource industry. So for Dr. Magnus Wettle, the floor is yours.
Thank you, Gabriela. Let me just open up my presentation.
Yes, it's clear.
Thank you. Okay, so we are down to the last talk of session 1, and I will grant myself the luxury of taking a step back to talk about the journey of SDB so far and where I believe it's going. So on that note, I think we, thanks to the fantastic talks we've already seen today, we have an idea of where SDB is presently. So we've had two navies show how they've stepwise or gradually adopted SDB data and eventually moved on to establishing their internal capability, and not to mention finding new ways to use SDB data along the way. So I think that's a very inspiring development and story. We saw Chris from the University of Queensland. He presented essentially a world first application of Earth observation data, satellite data, in mapping biodiversity at, well, I would call it national continental scale. Emily gave a great overview of all the different use cases for SDB, both in terms of location, but also in terms of the different sectors, whether it's environmental management or natural resources or navigation. And finally, we had Friedhelm, who from 7 Seas, who I think gave a very pragmatic or demonstrated a very pragmatic and effective way to use satellite technology for supporting navigation. So, but how did we get here? Well, it began, well, probably in the 70s, but the sort of serious references appear in the 80s, headed by LINZ, so-called empirical methods, which used essentially, they required some known survey data to tune the algorithm, which was initially based on linear regression, to tune the satellite data, if you will, and extrapolate the known depths across the entire satellite scene. And they were called empirical methods. And in fact, one of the early developers of this, Richard Stumpf, who's referenced here, he actually gave a presentation at our Americas and Europe SDB Day 2 weeks ago, where he showed an updated and more sophisticated way of applying empirical methods. So I urge you to watch that presentation when you have time. And the JEBCO cookbook has been alluded to by Captain Yanuar, another implementation of empirical methods. But I guess the thing is with one of the reasons to use satellites to map bathymetry is if it's a location you can't get to, or if it's too expensive to get to. And at the same time, you might not have any survey data. That could be the whole point. And that's where the physics-based methods came along. They essentially attempt to describe the entire system. So the light signal, as it travels through the atmosphere, through the water column, bounces off the seafloor and goes back up again. If you can describe that system fully, physically, in theory, you can see how much, or calculate how much water the light passed through, which is your depth. So these are the physics-based methods. And I guess the key point is that they do not require any survey data, input data, to be calibrated. So in theory, with a good sensor and suitable imagery, you can map anywhere on the globe where you can see the seafloor independently from the comfort of your desk. And there are some implementations here. So the key message here as a user or I guess provider of SDB is to know that the pros and cons of the two methods, and both have their fit for purpose niche, shall we say. The empirical method is typically easier to implement. And if you have good quality data, it produces good results and it's rapid and fast to use. The physics-based method is more complicated to implement. There's a schematic illustration here on the right, which shows the databases that go into it, the various correction modules that go into it, and eventually you arrive at depth. But the advantage is that, well, essentially what you're doing is you're understanding the signal from the ground up or from the sky down. So you can quantify your uncertainties and get a handle of the accuracy. So those are the two main categories of approaches. So that was, if you will, the theoretical or the academic evolution of SDB. On the real world side, this timeline represents at least how we've seen the evolution of SDB. So for about 20 years, it was in the R&D domain. And as far as we're aware, the first commercial SDB project that we did was in 2005 off the coast of West Australia. And that was around environmental management. So it certainly wasn't at the stage of supporting navigation when this was brought into the real world, if you will. But by 2012, we had national agencies like NOAA and the United Kingdom Hydrographic Office. They were evaluating SDB. And around the same time, marine professionals were using SDB data as well. Typically, the big players, when they first came in contact with it, they would evaluate it themselves with known locations. And in 2015, we heard from Commander Waterson, he mentioned this as well. We consider it a bit of a watershed event when the UK Hydrographic Office put some SDB in a nautical chart. Now, I'm aware that it was a very small area of SDB, and you could almost call it experimental, but it was still a significant step if you take into account the conservative nature of hydrographers. So, and the New Zealand Hydrographic Authority did the same 4 years later, where Emily referred to this in her talk in the Pacific, where SDB actually found its way onto some charts there as well. At the same time, the IHO, that's the International Hydrographic Organization, they updated their S44, that's their survey standards, updated it, and one of the remits was actually to to be able to account for or accommodate SDB type specifications. So this was another important step. And by last year, as we've heard now, there were 2 hydrographic agencies using commercial SDB software and establishing their internal in-house SDB capabilities. So yes, this has been the journey so far. And I guess the key thing that we've noticed, some of us have been around since the beginning, or at least the early 2000s, is the degree to which the uptake is not only increasing, but I would dare say accelerating, which is exciting. So now I'd like to address some of the things I see either developing now or in the future. So this I've already touched on, the survey standards. This is an example of the 6th edition survey standards, which was recently published, where it's now in matrix form, so you can specify the type of hydrographic survey you would like by picking your specifications according to the matrix, and it will now account for the type of performance that SDB can deliver. So that's a great development. And then we heard Friedhelm mention the CATSOC categories. So as opposed to survey standards, we have the issue with charting standards, where SDB, I would say there's still work to be done, perhaps find a better way of implementing SDB data in charts using CATSOC categories. So what we see here is that well, the red squares indicate where SDB fulfills a given category for a given requirement. So we can see that in terms of positional accuracy, SDB could be considered to be a CATSOC A1. And perhaps for the first 0 to 5 or even 10 meters of depth, it's arguable that SDB can be formed to A2. But if we're going to take the all the considerations into account and the full range of over which SDB can operate down to say 20 meters, then this puts SDB at a CATSOC C category, which perhaps doesn't quite fairly represent how SDB can be used and should be used. So this is an area to be developed together, and a good example of why we want to have these types of SDB forums where we can perhaps get together and work on this. So that's one area that I see developing or would like to see developing. The other area of development for SDB would be in the vertical accuracy. We've heard references to this throughout the talks. We have here an example, the same scene over a reef. The top scene on the left, you can see some haze in the atmosphere. It's been contrast enhanced. And the scene on the bottom, we see some turbidity in the water column. And both of these environmental parameters will affect your SDB output. Which you can see here on the right, you've got the SDB calculated for both scenes. So the same location should have the same SDB, and you can see that it doesn't due to these environmental parameters. So we've seen this schematic earlier, the different corrections that need to be applied to satellite imagery to try to get the best result possible. So for example, what's happening in the atmosphere, the adjacency correction of photons leaking into the signal, sun glitter, the absorption and scattering happening in the water column, all these things influence the signal. And as SDB has developed, I would say that it's been an incremental and gradual improvement on all these correction factors, which have gradually improved the vertical accuracy of SDB. And the ultimate goal is to, well, maximize it, but that will lead us to make more autonomous SDB algorithms and software, but also give us the transparency and traceability in terms of accuracy and errors. So,
Magnus, you've got 3 more minutes.
Thank you. So, but now I think we can almost talk about a step change, where this is a technique we patented a few years ago, and it's taken some time to develop. But essentially, it's a simple concept. We use the same algorithm flow to correct the data, but we process several scenes at the same time. And this allows us to have an additional constraint in our, I guess, reverse engineering of depth, and that is that the depth should be the same in all the scenes for a given location. And with this constraint, here's the same location again, we're able to improve our accuracy significantly. This scatter plot shows an example of almost all the data now inside the tolerance bounds of 50 centimeters plus or minus 10% of depth. And we have here another way to look at it. We have one scene at the top affected by sun glint. You can see how it affects the scatter plot. middle scene affected by turbidity and another scene affected by aerosols in the atmosphere. Whereas when we're processing all 16 scenes in parallel, if you will, with the additional constraints, we improve our accuracy. And this is without any in situ input calibration data. So we've taken I think, fairly significant step in improving the potential accuracy of SDB for a physics-based algorithm with no other input data. And that brings me to one more little topic, which is we now have a satellite orbiting us that's carrying a LiDAR system, which is acquiring transects, photon clouds, which allows us to get depth throughout the globe using LiDAR. It should be handled with care because, well, first of all, it's quite, it's not trivial to convert these point clouds into water column depth, but also there are errors in the ISAT data. That's the name of the satellite platform. So it shouldn't be taken as the truth either. But it does give us one more tool for getting a handle and validating SDB worldwide. So this ongoing journey of developments, where it's taking us is, as you've heard mentioned by Commander Waterson and Captain Yanuar, is software, which can work and provide reasonably accurate SDB results to enable in-house capabilities for users. And that's an important development. So what we have then is an improvement of accuracy, which will be ongoing, which will help us to make these approaches more simple and more autonomous. It allows us to make more robust and usable and user-friendly tools for SDB development for in-house capabilities. And this is a topic of session 2 coming up now. And there's also the topic of standards and best practice, which is an important ongoing journey, I guess, for SDB and its uptake in the industry. And that is the topic of session 3. So I like to think that we've covered on 2 of the more important topics and areas of development in SDB in the upcoming 2 sessions of this conference. So if you're here participating, you are essentially also sitting on the prow of this ship here, sailing on. Thank you.
Thank you very much, Magnus, for the wonderful talk. I would like to inform you all that we should have ended the first session by now, but we will allow 3 short questions in the session. So I've already got your questions from the chat box. Probably I'll just read it out loud now. So the first question is from Chris Roelfsema. The question is for Captain Handriono, Captain Yanuar. So the question is, for Indonesia, there is the one map policy initiated by the government, which is a good initiative. The question is, what implication does this have for mapping bathymetry of Indonesia with SDB? So Captain Yanuar, would you please answer the question?
Thank you, Gabriela. For the questions about the one map policy, the one map policy is different things. It's not related with the Hydrographic Office, but it's part of the national policy in order to provide references map for all of the agencies in the government and also in Indonesia. This presentation map is based on the compilations of several of hydrographic surveys and also from others inputs. But the thing is that the implementation of SDB is not yet used for this one map policy, and is also only part of the presentation of the agency to provide data for planning purposes and environmental management. So for the implementation of the one map policy, mainly in the scale of 1 to 200,000. So it's different things. But thank you for the great questions. But for us, the implementation of the SDB mainly for having completing the sum of the charted area to have additional data rather than nothing. Thank you, Gabriela.
Okay, thank you very much for the answer. And then the next one would be from Mr. Oke Dwiana. I think he's from the Hydrographic and Oceanographic Center in Indonesia. The question is actually for Emily, but maybe Magnus or someone else from EOMAP Australia can chip in. So the question is, with the technologies getting more and more advanced, will Watcor-X be able to produce deeper bathymetric data with a more reliable accuracy in the future? Thank you very much. Yeah.
Well, how long is a piece of string, I suppose, is one way to answer it. The more we can improve our accuracy, such as with multi-image processing, the more we can provide reliable data and the further down we can go. However, there is a physical limitation. SDB is simply physically limited by having enough signal to noise of sunlight reflecting from the seafloor. So it's not going to be an ever increasing depth improvement. There will be a physical limitation. But if you factor in the need for a certain given accuracy at a given depth, then yes, we will gradually get deeper and deeper within this constraint.
Okay, thank you very much. So Captain Oke, I hope it answers your question. And probably I really apologize for this, but this is going to be our last question, so we can move on to the next session. So the last, so there's actually a question for Friedhelm, but he has actually answered it. The question is from Dennis. Thank you, Friedhelm, for answering it. But probably we could just repeat it if you don't mind. So the question is, I really appreciated your presentation. Have there been any cases where groundings took place hitting uncharted shoals after they were SDB detected, but not charted or issued as navigation warning by the Hydrographic Office? So if you could answer this live, Friedhelm, thank you very much. The question is from Dennis. Yeah.
Yes, I answered the question, and yes, we are not aware of that such groundings happened after SDB data was collected, but as I said, we are in the process of building up this stay away database. So this is we're kind of at the beginning, and so we cannot report such cases. And there was another part of the question I haven't answered yet, and that part is if we are making this available to the hydrographic offices. Once we have finished our work, of course, we will approach hydrographic officers and get in touch with them to inform them about our findings. But we're not, we're still in the process of developing this database.
Okay,
thanks.
Thank you very much for the answer. So, ladies and gentlemen, we have come to the end of our first session, SDB developments and future technologies. Before we move on to the second session, I would like to thank everyone, every presenter in the session, to Magnus Wettle, to Commander Chris Watterson, to Captain Yanuar Handwiono, to Dr. Chris Roelfsema, Emily Twiggs, Friedhelm, Moggert-Kägeler, and everyone who has been involved in this first session. We hope the session is useful, and if you still got any questions, you can post the questions in the chat box, and hopefully we will try to respond it by the time that we are continuing this session. So thank you very much for your attention. We will now move on to the second session. Okay. The second session would be more technical. It's about do-it-yourself SDB, and we've got two speakers in here. The first one would be Knut Hartmann from EOMAP Germany, and the second one would be Christian Boedinger, also from EOMAP Germany. So without further ado, I will give the first talk to Knut Hartmann, which will deliver a talk about establishing independent SDB capabilities, tools, and software. I will read out Knut's bio for a second. So Knut Hartmann is the COO of EOMAP, and he's passionate in Earth observation, geodata expert, and in the position of Chief Operating Officer of EOMAP. Knut holds a degree in geoecology and a PhD in natural sciences. Prior to joining EOMAP in 2011, he worked in the geoinformation section of an engineering company, as well as the German Federal Research Center. Throughout his career, he has developed and applied solutions for different applications and across a range of industries. Amongst others, he was expert in advisor to an international law of the sea, or ITLAS. Kurt Case supports national benthic monitoring concepts on national levels and is leading the European Innovation Action to improve shallow water mapping. So, Knut Hartmann, the floor is yours. Your microphone is not on, Knut. It's still off. It's still muted.
Ah, now it works. All right.
Yeah.
Thank you. No worries. All right. So thanks, Gabriela, for the introduction, and thanks for the session 1 speakers. I think we all agree that in the session 1, we actually learned a lot. There's a lot of great applications actually going on in SDB in your region. So it's not only about bathymetry, it's also about seafloor. And I think it got clear that there are experts in the region, that there are ways to reach out to them. And that's well for a lot of you. I think this is a great information. So now you have points of contact to request information, request data. So for others, I expect that the first session has resulted in a big question mark. So the big question is perhaps, how can I actually do that if I want to do that on my own? How can I create SDB data? And that is the topic of this session actually. And it's the aim of the session really to guide you a bit of what is possible on a software and what is available and where are the technical where are we on a technical level. So I will do an introduction talk and then also directly introduce my colleague Christian, who is not here physically with us. So I have a recording which I will play following my talk. So just directly starting here. So the challenge if you want to do SDB on your own is there are, let's say, a couple of questions which you mandatorily have to address. So everything starts with image data if you want to speak about SDB, satellite-derived bathymetry. So big question is, how do you identify which data set is good, which is not good? So that's actually not an easy task. And then the next task, if you have data, how can I generate bathymetric grids out of that? Then if you have done that, you will have the question mark, okay, how do I know if it's good? If it's, how does it fit to reality? And the final question is, especially if you are a bit on let's say, on commercial pressure, is I can't do like a couple of years of research. I need to rely on something which is there already. So we have faced these questions many times actually by our clients, and we addressed these and developed software packages here. And before really briefly introducing them, I want to introduce you to the requirements which we defined in order to develop and provide those software services. So first of all is we don't want that those kind of software solutions can only be run by experts. So we want to make it easy to use. So people which have not a higher education, let's say in satellite analysis or image analysis, they should be able to use that. And easy to use also means that we do not want to have any other dependencies on any hardware or software for our clients. Yeah. So which means it should be affordable at the end, and it should be a great value for money, of course. And finally, yes, of course, the data needs, the outcome needs to be reliable. There needs to be a transparent process within all these processing steps, which at the end results in a standardized process. So those are the underlying concepts for the software which developed. Now I do a step back, actually, I said everything starts with satellite data, and that is not trivial, to be honest. So you might not know, but there are dozens of satellites which are in orbit, and the number is continuously increasing. And they fly around in fixed orbits and record every place on Earth several times per day, actually. So we have, yeah, really hundreds of millions, even more of square kilometers, which are recorded and archived by satellite data. Some are accessible, some are not. And the first task actually for performing SDB data is to identify out of all those data, those ones which are okay for your purpose, for your mapping purposes. So to guide a bit here, we developed an online tool, which I briefly introduce, simply describing it. It queries the archive, makes a rank if a data set is feasible for the purpose of SDB. So which means if there's cloud on it, if there's sunlit on it, if the water is too turbid to apply this technology. So the next slide here, it shows this tool. You only need your browser actually to do that. You will be able to query every place on Earth. Simply select your regions here. We demonstrated it here in the Caribbean, but it works everywhere. Send it to the processing, wait a minute or two, and the outcome of this tool is actually that there is a quality ranking, which we see in a second, a quality ranking for each of the archived satellite data. The higher the number, the better. So 100 would be perfect, such as this one, for example. There's a way directly to download the data as well. And of course, you can query the data for time and for quality. Yeah, so you can apply this as said simply by using your browser. It's a very easy helper, let's say. And it's actually very crucial because, as I said, everything starts with satellite imagery at the end. So at this point, we found a nice data set here in September for this given location. And that's a tool which really saves hours of your working time if you want to do that. But this really does not help you if you need to process the SDB, because you then start with raw data from satellite data, and then you need the tools to perform SDB. And for that purpose, we developed a couple of software. My colleague Christian will introduce Watcor-X, which is, let's say, our flagship software for mapping SDB in areas where you do not have any survey data at all. So I will not go into this one. This will be the content of the next talk. So the question is, after I've processed the data, how can I check if it's okay, if it's fits to what I expect it to be? So first of all, to directly say SDB data that is not a specific file format, that is very common. And if you run your hydrographic or GIS software with bathymetric data, you will be used to this. So we are speaking about XYZ data, geotiff data of this kind. So it's easy to load those data in the software solutions which you do use on a day-by-day basis. It's also important to understand that the depth measurements of SDB, they can come with vertical uncertainties. So these vertical uncertainties, they are modeled vertical uncertainties based on the sensitivity of the model itself. But every depth location comes with this kind of information, which will support the understanding here of the data. And as already mentioned by Magnus, there are ways where it makes the user also much more easy and comfortable to let's say to post-process and understand the data. So I just mentioned the multi-image data processing here, and Magnus also touched on the satellite LiDAR bathymetry, which is a separate piece of information borne by a space sensor, which can be also again incorporated or provided as a separate database. Finally, I want to stress the fact that all this software and also the Watcor-X, which will be presented in the next talk, really is the outcome of a long time and of systematic research. So we have undertaken all the pains of the development from an early start, and really have brought this kind of solution to where we are now, to a fully commercialized, tested, and ready to go solution, as we heard also from our keynote speakers, how they use this software in practice. So we now reached the highest technical readiness here, and as said before, it's really based on physics, which means it really does not rely on having training data or any empirical fits, which might not work for any region in the world. So this is something which is unique and which makes this software and our offer extremely unique. And we did a lot of efforts to make it very comfortable to use. So I mentioned Watcor-X already. So that's not the only thing which we offer. Watcor-X, I mentioned that it's a local software installation without training data, has a high untransparency here. But we are working on an online version right now, so we expect this to be published in summer this year. And the main purpose really of this physics-based approach is as a reconnaissance survey. You can plan your survey, bathymetric surveys, or you can use it as integrated survey concept. Yeah, Gabriela, noted. Thank you. Next to that, we have other tools. So we have the software which we call Watcor-X and the online portal as online web application as well. So that's more, let's say, for smaller areas where it comes to filling data gaps of survey data. If you have a single beam line survey, if you want to understand the morphology between your lines and want to expand your survey, you might simply use the let's say more flexible tool like Watcor-X here, or the software version. There are a lot of helpers which we developed over the years, and those are increasing. I mentioned already the tool which supports the image finding. There are tools to provide you assessment on water quality to understand on the feasibility for SDB, or actually also for LiDAR, if you wish. Magnus already mentioned the satellite LiDAR toolbox, and we are working on others. So tools for seafloor mapping and so on. So as you can understand, there's a lot of action going on here, and this development is not possible without getting your feedback. And that is why I'm very, very happy to see so many people of you in the room here and seeing this big interest in the stuff what we also do here. So what I want to point you is, I will share this link actually in the chat formula. I want to point you to the fact that there is a joint research project here by a couple of entities, which this project is led by EOMAP and co-funded by the European Commission meeting. There's the Survey Monkey. So, sorry, there's an online survey, which I want to point you to, which helps us to further improve the tools and our offers here. So I would really ask you to simply take 5 minutes of your time and help us here, because what we are really after is to provide the best solution for you as possible. So that's it. I will just skip this one. It's actually online here. I will share it in the chat, and you will find it also linked to the SDB Day page. That's it. Thank you very much really for listening. Gabriela, I will just do the quick introduction then, and just directly play the video for Christian. So the next talk is pre-recorded from Christian Boedinger. Christian has done this talk like 2 weeks ago when we had a similar event for the US and Caribbean time zone. Christian is here SDB expert at EOMAP. He has done trainings and capacity building for SDB software, actually more or less all around the globe. And he is really the go-to guy when it comes to SDB software. So without further ado, I would just stop my screen share and start it right away.
Hi everybody. So I will now present you a short tour to through our Watcor-X software, which is a physics-based SDB processing software, and the only one that is on the market right now. So first of all, we had a couple of objectives, core objectives for developing Watcor-X. First of all, we wanted to create a ready-to-use software that is working independent from any kind of survey data. And to do so, we implemented a fully physics-based workflow into the system that grants a high level of automation and requires only a minimum of user input to work with the data. So, and let's start right away. So in the following, as I've seen like a question in the chat before, asking if we need to purchase data to process SDB. So the answer here is no, you don't. I will use here open source and freely available data from the Sentinel-2 satellite, from the ESA, which has 10-meter resolution. And I will use this data as is, so in the raw form that everybody of you can just download as is. So let's start with just ingesting the data into the system and specifying where to save the results to. And now we set up the workflow, and we can have now a couple of configuration options. For example, we can decide whether we want to process on the graphics card or use multiple CPUs. And now you can also do some adjustments and configurations to the workflow in advance, but you're not required to. So you can also do this later on, or you can just process as is. And then the image will be loaded into the image viewer. So the scene here is the location from the Virgin Islands. And you can now draw your AOI, your region of interest, on the map canvas, or load your already existing AOI from your desktop. So I will load one AOI from my system into the map canvas, and I quickly zoom in a little to have a better overview. And now let's enhance the contrast to have a better view on where we find optically deep water areas. So areas which are optically deep. And the last thing we do is drawing some polygons over these areas for a reference. And now we are ready to start a process, and everything else is done automatically. The system will run through, and there's no further user interaction required so far until you can finally have a look onto the results and inspect what is the outcome of the software. So let's have a quick look on the results, which are stored in your specified results folder. And you have here a RGB display of the satellite image and a color-coded GeoTIFF of the SDB, and also some other files. But what you get out of the system is up to you, so it's configurable. These are standard files that can be used in any kind of GIS system and also in any kind of other software like Chimera. As we heard before, QA/QC processes are quite important to assess the accuracy of SDB processes. But if you have validation data available, or for example also the Atlas data, you can compare them with the SDB, but you're not required to. So this is an optional step, and I will just use in the following. Of course, you can also make a title correction. If you experience you have a title difference between the satellite image taken time and the validation source. And then I will import a validation LiDAR set from the NOAA and finally trigger the validation. And as we see here, That's the comparison between the SDB as processed as is without any further configuration compared to the LIDAR data set. So 10-meter resolution SDB compared to the high resolution LIDAR data. And we see we have already a pretty good fit to the one-to-one line between those both. 78% are within the standard boundaries of tolerance boundaries of 1 meter and 10% of water depth. But in the following, we will see if we can further improve the results by a couple of other options. So let's first take a deeper look into the data. So Watcor-X also provides the possibilities to for experts to take deeper look on the data, to view intermediate products, and to configure different steps. So as you see here on the right side of the GUI, the workflow control panel, every kind of step that is blue marked has already run through successfully. And we also have a ample system supplied here, indicating in different colors where the user might potentially pay attention to. So if I have a look here, I see that there's a warning triggered at the atmospheric step, indicating that I have a high aerosol concentration here. And I can visualize this in the software directly and see what the AOT concentration, so the concentration of aerosol optical thickness that was calculated per pixel by the software is like. So we have values of 0.55 here, which is quite high aerosol concentration, indicating that there's heavy atmospheric impact. So in this case, where I have this environmental limitation, it might be interesting to also have a look onto other data sets. And the same could be true if you have partial turbidity or a lot of boats in the scene. And to deal with this problem, we have integrated a multi-image processing into the software that is using different kind of scenes and process them all together to minimize this environmental impacts and thereby increase the reliability on the results. So as you know, or you might know, it can be a quite time-consuming process to look through all the data and filter out which satellite scenes might be useful for processing. And to do so, as already was presented by Edward, we have developed this Aeolytic Swift tool that might support you in your decision. So let's quickly have a look into how to set up a multi-image process. And you will see this is quite an easy thing to do if the process has already finished. So the process of the single scenes. So I will just switch to the multi-processing here and add some other readily processed scenes and import them into the Watcor-X software. I can now correct for the tidal differences between those scenes to bring them all on the same level. And if I've done so, the rest is quite straightforward. I just can apply those configurations and start the whole process. And now, as before, everything will run through automatically, and I just need to wait till the process has finished. If it's finished, I can validate once again to make sure that I have an improvement and that taking into account multiple images has increased my results. So let's repeat the steps we did before for the single scene and load into the LiDAR validation set for comparison with the SDB. And if we do so, we see that we have a pretty good fit between the Watcor-X SDB and the LiDAR depth which is 93% between a tolerance bound of 1 meter and 10% of water depth, which is also an increasement of 15% towards the single scene results. So in this case, we really got a quite huge improvement by taking into account the information from different kind of scenes. So as a short wrap up on this topic, you've seen Watcor-X is a ready-to-use software that requires a minimum of user input and has a high level of automation, being fully independent from surveying methods. You can just use them for validation purposes, if you like, due to its physics-based background. And it also has the possibilities to process multiple images to increase the reliability on the results. But it might be as well that you are not after a fully physics-based workflow because you already have a pretty good coverage on your data, so your survey data. So it might be handy for you to have something to fill those gaps. And here we also have a solution right at hand. It's called LINZ SDB, and it's an online tool that is working fully independent from any kind of hard or software. So you can even use it on your cell phone and trigger SDB processes on your cell phone to get the full coverage bathymetry. So this was just a short excursion. Of course, we have limited time options here, but if you want to learn more about this, you can contact me via email directly, or contact us via the contact formula on the SDB Day homepage. And you can also request a training or a discussion on more detailed questions on that site. So thank you for your attention, and I hope you can enjoy the rest of the SDB Day.
Okay, so thank you very much, Knut Hartmann and Christian Boedinger. So unfortunately, we won't have a Q&A session in the second one. So you can address your questions in the chat box, or you can also address the questions directly to EOMAP. I think someone from EOMAP will drop an email in the chat box, so you can all answer any questions that you're interested in. So thank you very much again to Knut Hartmann and Christian Boedinger. So before we move on to our last session, I would like to welcome Thomas Hege, the Managing Director of the EOMAP headquarters in Germany, who would like to say a few words. So Dr. Hege, the floor is yours.
Thank you very much, Gabriela. Yes, we have it's a short but very important message that will be made by my colleague, Pak Fajar, so the director of EOMAP in Indonesia, in a few minutes. And dear partners and conference participants, well, selamat pagi. On behalf of EOMAP in Germany, for me, it's a great honor that the collaborative mentality of EOMAP is from now on forced by colleagues and expertise from Indonesia. So visit the largest and maritime-dominated economy in Southeast Asia. Personally, I see this as a major milestone to strengthen the tight link between the further journey on technology development and applications, as we have heard right now. So just remember the wide and important range of use cases demonstrated by Captain Yanuar and the journey of EOMAP Australia, starting actually more than 15 years ago in various tight collaborations. So it's worth mentioning that these relevant introductions for Indonesia were made within the Hydrographic Commission meetings through the national representatives, Captain Yanuar, Captain Oke, with Admiral Hydro. So obviously, these regular meeting formats of the IHO with industry participation play a dominant role also for the economy development. The same does apply for the tight collaboration with leading research institutions. For Indonesia, the ITB, universities through Professor Porbo as leader in hydrography and geodesy and industry with geotronics. So we have a very strong ambition to grow a strong, experienced team in Indonesia. This multi-institutional collaboration is for us very relevant in this journey. So the topic of this conference is obviously this journey, and I wish all of us good luck building a strong high-tech Indonesian company with relevant impact on safety of navigation in the region and economic and ecological development. I would like to, with these words, I would like to introduce my colleagues who are managing the CEO of EOMAP Indonesia, Pak Fajar.
Thank you, Thomas. Okay, good afternoon. Selamat siang. Thank you, Thomas. Thank you, KB, and all the committees. Thank you for the time given to me to deliver this exciting announcement, especially for me and SDB users in Indonesia and also Asia. Listening to the information shared and exchanged throughout this day that came across from Asia and Oceania got me more and more optimistic about the groundbreaking step that we are about to initiate. But first, allow me to share you a brief introduction and background of EOMAP in Indonesia. Brought by Geotronics back in 2019, EOMAP emerged as an alternative method in shallow water bathymetric survey. We are proud to be able to support and work closely with Hydrography and Oceanography Center of Indonesian Navy, or Pusidrosal, and its hydrographic operations. Soon after, private companies from surveying industry had also introduced SDB technology and took benefit from it. And in collaboration with Pusidrosal in 2020, we have also successfully held an SDB webinar with the topic Satellite-Derived Bathymetry for National Interest, and found SDB as highly beneficial to the widely applied in many sectors. Indonesia is one of the world's largest maritime countries, with 75% of its territories covered by sea, has its own potential that comes with challenges in terms of governing its vast marine area under various applications. In his vision, the President of the Republic of Indonesia himself has this determined campaign to make Indonesia as the world's maritime axis. And this is something that needs to be supported by all stakeholders in the country. With the spirit to actualize the aforementioned vision, also to strengthen the existing collaboration of the stakeholders, government, industry, and academia, I'm here to gladly announce the establishment of EOMAP Indonesia, with me given the honor as the CEO. By becoming a 100% local entity with growing staff and capacities, I believe EOMAP Indonesia can cater the requirements of SDB data and deliver solutions in a better way. To exist among the stakeholders in the country will also enable us to take a major step in understanding better and constructing a first-class business relation and support to the country. Sorry if my video was off. In the near future, we will also be able to improve and develop the whole EO data ecosystem by having our own practical application ground and research base in Indonesia. We aim high, and by establishing EOMAP Indonesia, there is also bigger vision for EOMAP to be there in the Asia market. Hopefully, this will ignite a broader use and application of SDB technology in Asia. Thank you, Thomas.
Thank you, Fajar.
Yeah. Thank you, KP. I give the floor back to you.
Okay, thank you very much to Thomas Hege and Mr. Fajar S. Adi. Now we would be moving to the last session. So I will hand over the session first to Magnus. So Magnus, now the floor is yours.
Thank you, Gabby. You are now free. You've done a great job. So the last session, I alluded to it in my talk. One of the topics of standards and best practice use of SDB. That's what we'd like to ideally get a discussion going on this topic. because we feel that's something that should be done with the broader SDB community. So, but I'm very pleased to, first I would like to introduce the chair of this session. That's Professor Puerbandano.
Hello.
Who, yeah, hello. Since 2018, he's the Associate Professor in Hydrography at the Institute of Technology in Bandung. He's the Vice Secretary General of the Indonesian Hydrographic Council. And prior to this, he was a postdoctoral fellow at the Research and Technology Center in Bozen, Germany. And since 2010, he's involved in various national and regional consulting projects, mainly related to coastal and offshore mid-ocean industry. He was awarded the Honorary Surveyor A brevet from the Indonesian Hydrographic Office in 2013. And during his service as chair of graduate program in geodesy and geomatics engineering at ITB, he set up the IAHO recognized Caie hydrographic education program, where he serves as the program chair until early 2020. So, with great pleasure, I introduce Professor Puerbandano, who will chair this session. Thank you.
Thank you, Magnus. We have quite not very much time left, but I'm excited to bring this into you, and I am introducing Mr. Stuart Caie. Hi, Stuart. Caie Ora. I just learned that word this morning. And Stuart, I really wish I could be in the background picture, but unfortunately we cannot. No? Yes, Stuart Caie is presenting a topic on the LINZ SDB experience, charting SDB data. So let me read for you his bio shortly. Stuart Caie is a manager of hydrographic survey in the New Zealand Hydrographic Authority, which is part of Land Information New Zealand. After 16 years working as a hydrographic surveyor in the UK, Stuart moved to New Zealand in 2005 and joined Land Information New Zealand LINZ in May 2006 as a senior hydrographic surveyor within the New Zealand Hydrographic Authority. Stuart led the New Zealand Hydrographic Risk Assessment Project, an evidence-based risk lead assessment to prioritize future hydrographic surveys around New Zealand. The subsequent long-term prioritized survey program, HyPlan, was published in 2017. Stuart has responsibility for maintaining this program of work, which is delivered by a panel of 2 survey companies. Stuart is also working on a New Zealand aid program, the Pacific Regional Navigation Initiative, which is focusing on navigation safety aspects in the Southwest Pacific, where LINZ is the charting authority responsible for producing and maintaining charts for the Cook Islands, Niue, Samoa, Tokelau, and Tonga. Stuart, please, you are the only presenter of this session, so you have plenty of time as well, but please don't tell the other panelists. No? Go ahead, Stuart.
Thank you very much for the introduction. Hopefully my screen is being shared.
Yes, clearly.
That's great. Okay, so tēnā koutou katoa, and thank you very much for the introduction. Certainly been some very interesting presentation today, showing the use of SDB, certainly for a number of purposes, and it's quite useful being the last person up because you can pick up on what people have said and include them into your presentation and look very smart indeed. So the following slides give an overview of our experience with charting SDB data. It doesn't go into the acquisition side of SDB, which I believe was covered in the last SDB day presentation, and also Emily provided an overview as a case study earlier. So before I start, I'd like to thank a couple of colleagues of mine, Brad Cooper, one of our hydrographic surveyors, and Alison Cantrill, one of our cartographers who helped pull this presentation together, so I'm very much appreciative. Okay, so as was mentioned in the intro, LINZ is the primary charting authority for 5 Pacific Island countries, the Cook Islands, Niue, Samoa, Tokelau, and Tonga. And we produce and maintain the nautical charts. As you'll appreciate, it's a large area with very remote locations where access to traditional survey boats is difficult, and you wouldn't want to be putting people and equipment into uncharted areas. Hence, SDB was an obvious way to start improving the charts And again, Emily mentioned the Pacific Regional Navigation Initiative, an NZ-aid program of work funded by New Zealand's Ministry of Foreign Affairs and Trade. And this was the means by which we could carry out our survey activities required to improve the charts. So we've already incorporated SDB data into some ENCs and paper charts for Tokelau and the Cook Islands, and now our main focus is on Tonga. In Tonga, there are 5 charts that are still on fathoms, and one shown there on the screen, and on undetermined datums. But that is changing. Now, one of the outcomes from the program, the PRNI project, was to improve the nautical charts, and this started with SDB that was collected in 2017-18, followed by airborne laser bathymetry, and then more traditional multi-beam echo sounder surveys in targeted areas. So skipping forward then, I guess, through to what we do with the data now. We took a bit of investigation back in 2018, and we looked at what other hydrographic offices had done. In particular, we looked at the UKHO's use of SDB in South Antigua in 2015. That's the image on the top right of the screen there. We also looked at what NOAA and have been producing, and also what SHOM have been producing. And certainly SHOM have been using SDB for a number of years. So as you can see, all 3 portray the SDB data quite differently on the paper chart product. And our main consideration was, what does the mariner need to see, and how do we provide it to minimize clutter, both on the paper chart and a vessel's ECDIS, or electronic chart display and information system. In Tonga, there are numerous marine reserves and special management areas to be portrayed on the charts, as seen here in the magenta polygon line. So if we use the similar portrayal as for SDB areas, just like the NOAA example, then that could be causing more confusion to the mariner and too much clutter on the product. So we decided to consider SDB as essentially another survey source, or as Magnus put it, part of the survey toolkit, which didn't need to be treated too differently from any other survey data. However, to ensure the mariner has sufficient information, on the ENC, we use the S57 objects, metadata object MQual, and also the publication in MNPub to indicate the relevant information. So when the mariner does a PIC report on the ECDIS, ship's ECDIS, then he'll be shown with this text that talks about the satellite-derived bathymetry. So we decided to keep the wording for the notes on the paper chart and ENC to be quite similar, although not totally the same. And in the ECDIS note, on the ENC note, we refer to the MQual, which contains an attribute, the category of zone of confidence, or the CATSOC rating. We also discussed maybe attributing the quality of sounding attribute on individual soundings, and maybe putting it as a value 4, which relates to an unreliable sounding. But really this would have taken quite a bit of effort, and possibly caused more clutter, more information to filter through. So keeping it simple, we just related it to the TechSAL and also the CATSOC rating as well. And what something has been touched on in some of the questions is really around the education of mariners in understanding these attributes and what the information mean, with very scant information provided or a description provided in the PIC report or in the information. Then education for a mariner is key for them to understand these objects and what they mean. So on the paper chart, we also now show the SDB in a similar manner to the UK, using a source data diagram and a chart note describing the accuracies of the data, and a reference to the Admiralty publication, the Mariner's Handbook, for further information about SDB. This is also similar to that shown earlier by Captain Yanuar from Indonesia. And again, removing confusion and clutter by not encompassing the SDB area in a magenta polygon. As you can see here in this image, for this particular approach to the port, then there are already quite a few magenta lines, one covering a special management area, and then another a non-anchoring area in the approaches to the port. So that's how we've presented the data. What's gone on behind that is looking at the data sets and merging the data sets. We had a combination of SDB to start with, followed by laser bathymetry, and then multi-beam bathymetry to follow that. So if it's just purely SDB, then relatively straightforward to chart the depths from that data set on its own. The challenge really comes in when we're overlapping data sets, and how do we manage some of the vertical differences that we see as you combine the data sets. We use Caie's Bathy database as our bathymetry processing and archive, and within that you got the ability to run deconfliction rules and set which data set would take precedence over others. So certainly there's noticeable vertical differences between the two sets there. As you can see, the color coding on the left hand side there, where we have the ALB overlapping with the satellite-derived bathymetry. Then taking that a step further, producing contours and depth areas. Even though there may be some relatively large vertical differences, the contours still look pretty okay. Particularly if we then clip the SDB data to around about the 8 meter depth to take out some of those larger discrepancies. So the contours were made from a more generalized surface, a Caesar file from Bathy database, and then the sounding selection was made from the pre-generalized surface. So the contours are a little bit more smoother, and then the soundings are fitted around that. So here we can see, hopefully maybe the grey is not coming out too well. On the left-hand side there are the soundings or the depths selection from the SDB coverage. And you can see that if you were to do the usual contour intervals of 2, 5 or 10 meters for a nautical chart, then you certainly see some odd shaped contours around the edge of the A or B coverage. So what's been the outcome? So as of today, we've produced a new ENC for one of the Tonga areas, still working. So the image there shows a bit of a swipe between the current paper chart, which is in fathoms and on undetermined datum, and on the right hand side there, the new ENC product. So by the middle of the year, we're hoping to have 2 more ENCs to be published. That will then mean that all of the old charts in Tonga that are on fathoms or undetermined datums will be replaced with modern charts. So thank you for your time. That's where we're up to, what we've been doing, and some of our learnings. It would seem that we're not the only ones in the way that the data is presented, and portrayed. But it will certainly be interesting conversations, I think, for setting up a work group or understanding what are the best practices or good practices for displaying and portraying satellite-derived bathymetry on these nautical products. Thank you very much.
Thank you, Stuart. Very effective presentation. You could witness that LINZ is among the first hydrographic offices implementing this. I think it was back in 2017, as you said, right, Stuart? And I would like to announce a little notice here that close to the end, before the closing of the entire event, we are going to have a poll session, and we really would like to invite all the panelists and participants to participate in that poll. And the poll will be looking at an idea on how the demand in standards and best practice of SDP shall be better documented, let's say. And of course, at this stage, we haven't decided yet how and what we are going to do, but at least we feel that there is an importance to go into this direction. So I guess Your opinion counts. And I would like also to thank all panelists who are still here. And I believe this brings more flavors to this session. And if you have any things to question, let me check the chat if somebody is delivering your question, or I might go back to the earlier question which is not addressed.
We do have time for questions for Stuart, so I welcome anyone with questions.
Yes, of course, yeah. So we welcome questions. I have my own question actually to Stuart while waiting for the other question from the audience. Stuart, while you have the capability with ALB and multi-beam echo sounder, of course, has a limited capability in this non-navigable area. What is the purpose of still using SDB to complement your ALB?
So the project was obviously output was to improve charts, and with the Fathom charts and undetermined datums, many of the islands are out of position. So the first up was to use the SDB data to, in terms of to relocate the islands, so to say, so to improve our planning. So we initially started planning SDB. We have an idea of the coverage and extent for ALB and then also multi-beam echo sounder survey. So as we collected the SDB data, we then paused, saw the results, located the areas, the charts, the islands, so that we could then reposition the coverage required for the ALB. So rather than flying ALB in areas where it's not needed, it's too deep, or we could then reallocate some of that flying time to areas where maybe the SDB has identified another shoal or area that hasn't been already picked up, so we can include it in that campaign. And then again, the same process using the ALB to tweak and adjust where we program the multi-beam echo sounder survey.
So it's a sort of planning, like survey design, and instead of using the data itself for to put into the chart.
I think initially it was a planning, but I think from the outset we were going to be using the data. Certainly, Tonga in particular covers a very large area. Many atolls and islands that are maybe only currently charted on a Fathoms chart, and they're not necessarily on any other scalar chart. So having that data to be able to portray that information on a WGS-84 datum, then that obviously makes it easier for us, able for us to then produce an ENC for the vessels to navigate safely around the archipelago.
Thank you, Stuart. Yeah, we have one question from the audience, Vanessa. Stuart, kindly please comment on that. The question is if there are best practices written anywhere for using SDB for modeling applications, aside from considerations regarding water quality and etc. Actually, the question is from all panelists who are still here, and if we have time, of course, I would like to invite them as well. Do you have any comment on that? I think this has been also my question as well. If you have, at least in your office, there is a formal guidance, official guidance on the use of this SDB data. Please, Stuart, thank you.
So for us, no, we don't have any formal guidance, and I think we're still relatively new to SDB world, and we've been fortunate enough that the project in the Pacific was an ideal area for running SDB. So we don't have any internal guidance. We use specifications that had been put together, I think, by the UK HO in previous years. So taking that as a starting point for us to then develop our own specifications for data collection and the data deliverables. But again, that was really purely for hydrographic purposes and updating nautical charts, which may be quite different for modeling applications.
Thank you, Stuart. So Vanessa, that was the comment from Stuart. Or perhaps one of the panelists is willing to comment on that. Dr. Chris Roelfsema, if you are still here. Captain Yanuar. Emily is not there anymore. Friedhelm, if you have any comment, please just turn your video on and speak up. The question is the official standard or document followed for this kind of work in addition to modeling. But anyway, while waiting for another comment, I would like to read the other question, Stuart. If you have any example of SDP data comparison in South Asian region, yeah, in Indonesian water, where water clarity is low, does those data matching the 1 meter plus 1% depth criteria? Maybe Stuart first. Anyway.
So we've run some SDB tools within the office for some reconnaissance and planning work. It's been using the JEBCO cookbook approach, and we've been getting some reasonable results. And realistically, around New Zealand, we don't have the same clarity water in other parts of the Pacific, so that could be a comparison to other South Asian areas where there is a poor water clarity. Top of my head, I'm unable to say what what in terms of accuracy had been achieved with that, but we were certainly getting some reasonable coverage, and that was particularly down in the south of the South Island. But again, it's going to be quite limited in terms of turbidity, water clarity, as to what can be achieved. I'm not sure whether Magnus may be able to say in terms of the comparison between the two processes, whether there will be a difference in what can be achieved.
Thank you, Stuart. I saw Friedhelm shows a case from Sunda Strait, Indonesia, and I still remember also Thomas. We tried something in Pulau Seribu, Pulau Pramuka, where the turbidity is not as good as what Stuart has in New Zealand. Do you have any comments on that, Thomas? Yeah, the depth accuracy, if it still follow 0.5 meter plus 1% depth in a turbid water, like what we have in Southeast Asia.
Oh, in turbid waters, of course, that's not possible. So there, as Magnus mentioned, there are physical limitations, various, so the depths, the optical conditions in water itself. So these high accuracies are possible under good conditions, or so better clear conditions, or if you apply multi-image processing, where we can actually consider then the various also the variability on water conditions and better. But Magnus also might note for this how this is then under Australian conditions. I would like to go back also to the question from Vanessa. So the gap of the best practices book. So because we are asking here about what is the experience under the different locations and with which methods and best practices we can improve those. And obviously we are here on a journey, and I would like to highlight that this question is very relevant to take up and build such a best practices guide and further develop this. Of course, it's as with other technologies. I think that's an important task that we should have on our screen and actively, for example, launch then such a working group or to continue this journey with, for example, under lead of universities.
Thank you, Thomas. Magnus, want to add something on this?
Yeah, I think that that brings us nicely to what we wanted to take a few polls here to get some feedback from the audience, and this was the first topic. I guess before the poll, I just wanted to check in with Stuart if you have any plans to internally develop how to chart with SDB, or if this is something you're looking outwards to see what a community would evolve.
We would certainly look to develop it internally for just as has been used, I think, by Australia. We're talking about using it as a reconnaissance tool and that risk mitigation, and how does that feed then into planning for future hydrographic surveys around New Zealand coast. Obviously, waterborne activities can be challenging. So the reduction, if you can reduce the amount of area to cover by a boat, then that's obviously a good point. I know others within New Zealand have used it. I believe NIWA have used SDB for a few projects as well. So and also defence for obviously for humanitarian purposes, but also survey planning or just similar to the Royal Australian Navy. So I think there is a community of sorts, different purposes, different requirements. So having some kind of best practice, whether one fits everybody or not, or whether there needs to be certain branches within that best practice that will cover off the various purposes.
Thanks. Okay. Well, I think we could launch a poll on this topic. Knut, do you have one ready? So the poll question will be, everyone can click on an answer. Do you see a needs for standards and best practice to be developed for SDB? And the answers you can choose from are yes. Sorry, I've skipped the first poll question here because we got onto this topic, so I think it's more appropriate. Mandatory, you have to have it. Yes, you would like it, but it won't stop you from using SDB. It does not affect you either way, or you just don't know. So we'll take a minute to collect everyone's clicks and see what we get.
Just a comment: the panelists, they will not be able to use the poll. It's just for the participants. Don't worry, and the results will be shared following the poll. So we will give the people a minute or so time to respond, and I can track and will stop it and share it after the majority has been able to vote. So I still a lot of activity, so the poll will still be open for a minute.
Is Friedhelm still here? I'd be curious to his requirements for standards or non-requirements. He might not be here.
I might excuse Friedhelm. It's a very early start for him. So he's based in Hamburg, and I guess he's searching for his 5th coffee of the morning.
Fair enough.
Magnus, perhaps we shall also in between provide a notice that a check form is available for them who are interested in joining to talk about this further, no?
Yes. So first of all, the polls here, I see half of the audience already used the poll. I will just give it a few seconds here. So just also to mention, we had about 120 participants on of which 90 are around still. And I see that half of them already used the poll, still increasing actually. So I will give you a bit of time to do that. So I mentioned, or my colleague Christian mentioned, that at the sdbday.org page, in the contact tab, you find a formula where you simply get in touch with us, register your interest in tools or actually in data as well. And what we are launching is a best practice working group of some kind. We want to do this really as a truly international kind of working group. And we have received requests from colleagues from US and Europe after we have had a similar event 2 weeks ago for the US and Caribbean and European region. So we want to bring those experts together here. And I would therefore really foster you to go to the webpage, register your interest in participating, actively contributing and participating in this kind of working group, which I think would be an excellent outcome. So I see I will stop the poll right now and share the results with you. Okay, you should be able to see it right now. Turbo, Magnus, one of you will go over?
Yes.
Mandatory at 43%. Yeah. Oh, sorry, Turbo.
Sorry. Yeah, just I am just interested in looking at that first question where we actually know from the participants list, but it is also interesting to see that 20%, more than a quarter of the participant is coming from the safety of navigation business. I think it's more in the hydrographic offices, mapping agency, something. No? And it's also interesting to see that environmental management, oceanographic and climate modeling share more or less the same. So I guess this is perhaps the direction of the utilization of the SDB data. Thank you, Magnus.
Yeah, sorry for interrupting you. Yeah, you're right. And I'm quite impressed, or it's quite noteworthy that a full 40% consider standards and best practice mandatory for using SDB, which certainly argues very strongly for developing this such in a sort of a broader forum environment, community environment. And indeed, if I look at the answers to the third poll question, there's a 60% willingness to participate, which is almost astonishing, considering that will involve some degree of initiative and interaction. So that is fantastic to see. And I think that's one of the outcomes we'd like to see from this third International SDB Day is if we can sort of get enough interest and at critical mass, people ideally registering through the web form for such a working group to discuss such topics. I don't know if anyone else would like to comment on this, but I would very much like to see that happen and evolve in a forum type environment.
I guess we have a collection of experts here in this session, in this event, because if you see the questions, the answer for poll number 4, number 4, although this is a multiple choice, they really attacking the things that require the improvement, which is the vertical accuracy, or not, Magnus?
Yep. I would say that's, well, it's also insightful as in where the investment should come in working with SDB technology, that vertical accuracy. And indeed, that's great direction to take for us to know and to work together to work towards that. And so you're right, we must have a fair amount of experienced users taking part in this poll.
And looking at the answer from question number 4, there are still 40% who are still, although not majority, but it's I believe this is more a broader application of SDB. because the hydrographic offices, they do really know how to deal with that. But there is still left a percentage of users who do need sufficient information on the use of SDB. Or not, Magnus?
Yep, I believe that's correct. And yeah, of course, we would very much like hydrographic offices to be part of this community and to really help drive both the requirements, but also the standards, and to develop best practice. Indeed. Thomas, do you have any comments on what you can see for the Australasia region in terms of these polls?
It makes sense to link this to a similar request was sent as the SDB Day Americas 2 weeks ago. And with a very similar outcome, so with a very strong ambition and also discussions with the hydrographical offices in the region around exactly that point, that they are wishing to contribute, actively contribute to such a best practices working group. So for me, this is the same, again, a call for this collaboration on this working group, which we now have to structure. And I think I might forward this to Knut, because he will summarize this maybe also as in the contact formula for all people and organizations who now want to actively contribute, that we can launch this exercise in this collaboration here around. So I think it goes even beyond than Asia and Pacific, because, yeah, for example, we had the comment from, I think, from David Wyatt, so from IHO. Then of course there is this interest as well now to launch this, because then it can be a practical working group and should be so, but it can be as well, of course, under IHO.
Do you have a view on that, Stuart? Do you feel that IHO should be involved?
Well, I think they would certainly have a vested interest in it, and certainly if we're looking at the JEBCO CIBA 2030 initiative, and what that is driving for, then this certainly plays a part in it.
So I think
Sorry.
Excuse me, Captain Yanuar, please.
Thank you. For this working group, I think we need some sort of guidance first in order to do the priority based on the inputs from the pools that we have, and then also maybe seek for the best expertise that can lead the guidance for the regulation adoptions, and also technical development, and also future expectation from the pools, and hopefully we will have a much better narrow and focused outputs for the working group. That's only things that I can comment on this stage. Thank you.
Yeah. So Magnus, I guess we have to thank Stuart for presenting this in the session, and I can hand my responsibility back to you. Thank you.
Thank you very much, Professor. Knut, did you have something to say? Or I heard you started speaking before. I'm just checking.
Always have something to say, but
okay.
often meaningful.
On the topic.
Meaningful. No worries. No. So I'm to conclude from the U.S. America's Caribbean Day, which might be of interest. We did similar poll actually with similar results. There is a need for standards to without obviously really knowing how this goes. We know, of course, there's improvement in S44 to adapt to new technology, which does not help to manage through the jungle of different SDB solutions which are around and provide guidance to those users which want to apply that. And this is something which we see actually quite intensively. And this is something which we believe needs to be addressed. And it would be wrong if we assume just to respond it from a single point of view, because what we also see in the review polls is that SDB has so many applications. Safety of navigation is just one out of them. So this is a topic which and needs to be also addressed in this kind of best practice guides. So the intention is to get the ball rolling. Yeah. So that is the reason why we are looking for this interest in the participation in this working group, and truly understand this kind of group as an international group which want to drive the innovation without really committing at this stage, because I understand this is hard for some entities, but it's to get the ball rolling, and it's a journey, and we have good cards to play it. So let's simply go for it. That's my saying.
I like it. Simply go for it.
Friedhelm is there. He raises a finger. He's awake again.
Oh, now you can hear me, I guess. Yes, talking about standards and bringing this to the IHO, you may be aware that there's a special working group at IHO, the Data Quality Working Group, that is dealing with standards about data quality across different IHO products and product specifications, which are based on the new IHO standard S100, but also on the old one S57. So this may be a platform to approach this working group and get in touch and make sure that the standardization process on IHO level considers what this group can contribute, and make sure that in future standards, SDB data, or the quality of SDB data, will be much better represented than what can be done today with the CATSOC, which has actually doesn't really, no CATSOC category really fits to all the characteristics of the quality of SDB data. So my proposal would be to approach a suitable working group at IHO.
Yep, I agree. As Knut alluded to, there will be applications of SDB that are outside kind of the IHO remit, where perhaps best practice still needs to be established in a separate group. But where there is overlap in terms of navigation, then definitely there should be an exchange, an approach, or even working together. Thank you. Okay. Well, I also would like to comment that I saw in the last question of the poll that 60% felt that they had enough information to use SDB, which, again, that's astounding. I don't think I would have seen that number just a few years ago. So that's really fantastic to see. Of course, we'd like to get it to 99%, but one step at a time. Anyone else have anything further they would like to mention? Everyone's good? Okay. In that case, I will conclude our SDBTA conference. I think there's been a lot to absorb today. I consider it to have been very rewarding. Great presentations and the input. I like to think that we've all learned something about the technology, and not to mention perhaps get inspired about some of the future potential that we've seen here today. And again, I'd remind those interested to consider ticking the box on the website if you would like to at least stay informed about the working group, but ideally contribute on standards and best practice for SDB. So thank you all, speakers and panelists, for contributing to this event, and to all the participants for helping us in developing this, I guess, growing community of SDB users and providers. And we'd like you all to feel free to get in touch with us. So with that, I'd like to say thank you. And if anyone else wants to say something, you're welcome. But thank you very much for coming.